Dame i gospodo, ja bih vas zamolio da zauzmete mesta, već je vreme da počnemo sa ovom sesijom. Hteo bih da pozdravim sve prisutne i da kažem da, kao i ranijih godina, nemamo mnogo prisutnih, ali su zato ovi koji su prisutni odabrani. Voleo bih da pozdravim predsedavajuće. Tu su gospodin Pearson iz Engleske, iz Škotske, čuveni stručnjak specijalno za rashladne sisteme i amonijak, gospodin Pachai iz Danske, koji je godinama sa nama i koji je juče dobio specijalno priznanje od KGH društva kao jedan od vrlo priznatih i poznatih stručnjaka iz ove oblasti. Treći je gospodin Koeppen iz UNEP-a, koji je zajedno sa društvom za KGH, znači UNEP, Ministarstvo ekologije, su organizatori ovog foruma i oni nam svake godine, već duži niz godina, pomažu u organizaciji ovog skupa. Ovaj skup se odnosi na nove tehnologije u tehnici hlađenja i mi sada pokušavamo nova iskustva iz zemlje i sveta da prikažemo učesnicima ovoga skupa. Ja bih sad zamolio gospodina Endija, pre nego što počnemo sa prezentacijama, imamo pozdravnu poruku gospođe koja je novi direktor u Međunarodnom institutu za hlađenje u Parizu. Poznato je da država Srbija pre više od 100 godina je bila jedan od osnivača tog instituta i mi godinama imamo dobru saradnju sa njima. Gospođa je ove godine pre par meseci preuzela dužnost direktora i ona nam šalje pozdravnu poruku koja će trajati par minuta.
Esteemed colleagues and distinguished participants, it's my great honor to open the 55th International HVAC in our Congress and exhibition, and I would like to thank you all for taking part of this event and take this opportunity to extend my heartfelt gratitude to Professor Branislav Todorović, President of the 55th KGH Organizing Committee, and Professor Bratislav Blagojevic, President of SMEITS. This annual event is a testament to the vibrant and innovative spirit of the HVAC in our community, bringing together experts, engineers, researchers and professionals from Serbia and around the globe. We meet at a crucial moment. The escalating climate crisis is reshaping our priorities and emphasizing the pivotal role of cooling and heating systems. Rising global temperatures and the increase in extreme heat events are driving a greater demand for cooling. So by 2050, the global energy demand for cooling is projected to rise by 45% compared to 2016 levels. This growing demand comes with challenges. More installed HVAC in our systems mean higher energy consumption and potentially more greenhouse gas emissions, also associated to the use of refrigerants. It's then our shared responsibility to ensure that HVAC in our systems are properly designed and optimized not only to meet the demands, but also to do sustainability. Energy efficiency, innovative design, and adaptability to extreme heats and the climate change events must be at the heart of the proposed solutions. Equally important is the role of heat pumps. These systems are key to decarbonizing the heating, reducing emissions, and also achieving the energy security, a goal that we must prioritize as we transition to cleaner and more sustainable energy systems. This Congress offers a unique opportunity to exchange knowledge, discover cutting-edge technologies, learn about innovative solutions, and forge collaboration as well that will shape the future of our research, development, and industry world. I encourage each of you to make the most of these discussions and connections, and I do invite you all to join the International Institute of Refrigeration. By becoming a part of our global network, you can contribute to advancing research and innovation in our field and also help us to address the environmental and energy challenges of our time. I wish you all a productive and inspiring conference, may it spark with many new ideas and also foster meaningful partnerships and guide us to more sustainable future. Thank you everyone, and hope to see you soon physically in the next event. Thank you so much.
Good morning. I can see last night was a tough one. There's not so many of you here, but thank you for coming anyway. It's a great pleasure to announce the first speaker is Andy Pearson from Glasgow, CEO of Star Refrigeration, and a very experienced and well-known person. The floor is yours.
Thank you, Alex, and congratulations everybody for getting here early this morning. It's great to see so many in the room. As Dr. Alush said in her recorded message, this is very much about sharing information. So I would like to share a couple of experiences from the UK relevant to our overarching theme this morning, which is improving energy efficiency in climate and ozone-friendly latest refrigeration technologies. So this is an introduction to the rest of the speakers that will be coming along and a little bit of case history. So moving along, there are three specific challenges that I would like to focus on that are facing the refrigeration industry and particularly the refrigerated logistics industry. The first is in the energy supply, where electricity is becoming more expensive and electrical supplies are less reliable. And what I mean by less reliable is as we move more towards renewables, there's a greater challenge of the intermittency of supply. So that maybe today the wind is blowing strongly and we have a high generation capacity from the renewables, but tomorrow it's a flat cam and there's very little happening. This is difficult to deal with. So efficiency of the refrigeration system is a key factor there, and we'll be talking a bit more about that through the rest of this morning. Climate change is the second challenge, and increasing ambient raises the heat load peak and makes systems less reliable. So resilience is the key question there, the key word. And then the problem that we have with persistent pollutants in the atmosphere and the ongoing environmental challenges that we face, we cannot be sure that the working fluids we're familiar with will be available in the long term. It's a process of continual change that's been going on for the last 40 years and will continue to go for many years to come. So the longevity of the system is the key point there. If you're going to be investing in a new system, you want to make sure that it's going to pay back over a significant period of time. So these three challenges, efficiency, resilience, and longevity, are really the topics that I'm focusing on with these case studies this morning. And the questions are, how can we address all three challenges with one action plan? That would be nice, you know, a one bullet, three birds type of approach. Can we afford to do it, and can we afford not to do it? Very, very important questions to address. So I want to talk a little bit about the persistent organic pollutants. I mentioned this yesterday in the keynote talk, so this is just a quick summary. Polyfluorinated alkyl substance is defined as a carbon chain which has got either two fluorine molecules attached to one of the carbons in the middle of the chain, or at the end of the chain, three fluorine molecules attached to the end of the chain. So that's what the little cartoon is showing here. If a chemical fits that description, it is a polyfluorinated alkyl substance. And in terms of refrigerants, we've been brought up to see things like R12 containing chlorine as a bad thing, and R404A with high global warming as a bad thing, one single number metric. But some of the things that have been introduced to us over the years as the good guys actually fit this description of PFAS. So R134A, for example, is a polyfluorinated alkyl substance because it has the 3 fluorines on one end of the molecule. Both 1234YF and 1234ZE are polyfluorinated alkyl substances for the same reason, and likewise R143A. So a lot of these refrigerants that we've been familiar with and used to using are now coming under fire with new regulations being developed specifically about the products of degradation, and this creates great uncertainty with regard to what is actually going to be available in 5 years' time, 10 years' time, 15 years' time. Interestingly, 2 refrigerants here that have been quite widely used either as single components or as blends. 152A you're perhaps not so familiar with. It was originally proposed as a replacement for 134A in car air conditioning systems, mobile air conditioning. Global warming potential at that time of about 140, so it just managed to slip underneath the threshold of 150 that was set in the MAC directive. And of course R32 with GWP at that time of about 675 just managed to slip underneath the 750 threshold. Interestingly, in the 6th assessment report from UNEP, the GWP of R32 is now assessed as 770, so it's actually just slipped slightly above the threshold now. And that's part of that uncertainty that I mentioned earlier. But you need to bear in mind that these numbers have a very wide tolerance. So if it's 140 plus or minus 20%, or it's 770 plus or minus 20%, having a fixed number threshold doesn't actually make an awful lot of sense. Better to get right down to very low GWP. And some changes to the refrigerant supply. Again, I spoke briefly about this yesterday, but I want to highlight a couple of things. I'm talking about the phase out of HFCs and possibly HFOs as well. On the other hand, you can see some of these refrigerants will be available in the long term into the future. So if we're talking about security of supply, we should be focusing on these things that have been with us for a long time, and we're not going to learn anything shocking or new about their environmental performance. So I want to talk about energy use, because really that is the core of the presentation. And everybody says that reducing energy is their top priority, but you have to judge them on the basis of what they do rather than what they say, because they say one thing, but their behavior indicates that their priorities perhaps lie elsewhere. And reducing energy use is definitely nice to have and very important to them, but top priority, I really don't think so. Staying in business, I would say, perhaps top priority, and everything else flows from that. There's still a massive variation from one site to another. I'll show you a graph in a minute that ought to really shock you. If it doesn't shock you, then I'm not sure that you are actually thinking at all. So I'll show you. The graph shows the measured kilowatt hours consumed per year divided by the store volume. Remember, we're talking about logistics, so this is warehousing, this is cold stores we're talking about. And it gives a very useful benchmark for comparing one site against another. You could use the floor area, but this can be a bit misleading because now we have high bay warehouses with a very small footprint, but a large volume. So actually the volume is a better metric for warehousing. And studying best practice figures from all around the world very interestingly shows that best practice doesn't vary very much as you move from one climate to another. If you're doing all the things that will deliver best practice, you will hit the mark irrespective of pretty much where you are in the world. So there are 4 factors that I grouped together here out of the 5 factors that I consider to influence the energy performance of a warehouse. And 4 of them, the utilization of the building, how busy is it, what the weather's doing, how good condition is the building fabric, is the insulation in good shape or is it quite degraded, and how do the management run the building, how tight are they on the process. For example, do they permit product to come into the cold store much warmer than the store temperature, or do they actually manage that process and insist that goods are delivered at temperature beforehand? These 4 factors all determine the magnitude of the heat load. If the insulation is poor, there'll be more heat gains. If product comes in warm, there'll be more heat to extract. And they're independent of the COP of the fridge plant. So it doesn't matter how good or bad the fridge plant is. If you don't get these 4 things right, your energy bill will be high. But the 5th one is the refrigeration plant, only one out of the 5 factors. And the performance is based on the coefficient of performance of the refrigeration system, which for many years people have thought, well, that's all that I need to worry about is a good COP. I'll tell you one way to get a good COP in a cold store is to leave the door open, because then the suction pressure will rise, the compressor will do a fantastic job, the COP will look really good, but your energy bill will be through the roof because your heat load is so high. You have to balance all 5 of these factors, attack all 5 of them to get a good energy performance figure. And that means it's not only about the refrigeration plant, it's about all these other things as well. They all have an influence on the amount of energy needed to maintain the store temperature at the desired value. And that's a key metric that we perhaps have misunderstood over the years. You know, if the room is cold enough, then everything is okay. Not necessarily true. The room might be cold enough and the energy bill is through the roof. So we need to be a little bit more intelligent about analyzing the information than that. So here's a question for you. If you bought a car and the dealer told you that the car required 5 litres of petrol for every 100 kilometres, you would think that's a pretty good fuel efficiency. You know, I quite like the sound of that. If the car that you drove away actually used 50 litres per 100 kilometres, you would be pretty upset. That is not the car that you bought. That's not what you paid for. You would be outraged, you'd go back to the garage, you'd demand your money back. Why do we accept that level of discrepancy in refrigeration system energy performance without questioning it? And I'll show you what I mean by that. The question is, how bad would the performance need to be to actually motivate us to do something about it? So here's the graph that I mentioned. The line at the top is the average energy performance per kilowatt hour per cubic meter of store across 700 sites all over Europe, measured round about 2013 and presented at the IIR Cold Chain Conference in Paris that year. That's the average. That's not the worst. That's the middle of the pack. The heavy blue line at the bottom is my estimate of best practice, what best practice looks like. If you look here, this is a store of 250 cubic meters volume, and this is a store of 250 cubic meters volume, 6.5 kilowatt hours per cubic meter per year, or 65 kilowatt hours per cubic meter per year. That's the difference between 5 litres per 100 kilometres and 50 litres per 100 kilometres. That's how shocking this graph is, and you really need to be paying more attention to this, because that average is not acceptable. So what excuses could there possibly be for accepting an average that's as high as that? Some people might say, well, my plant's not really that bad. The room is cold enough. You know, the product isn't being spoiled. That's my measure of success, is the room cold enough? That's not good enough. I can't afford the capital outlay to improve the plant. That's another excuse that you might hear. I know that I've got a problem, but it's just too complicated. I don't know where to start. I don't know how to improve the plant. I can't afford to take it offline to make the improvement because the product throughput just keeps coming and I don't have time to make an intervention. Or maybe a slightly different excuse, my contractor takes care of that. I trust him to do the right thing for me, and the room is cold enough so I know he's doing a good job, everything is okay. None of these hit the mark. These are all mistaken thinking. So here's a first case study. This is a warehouse in England which is used for supplying a restaurant chain all over the country, and it had a pumped ammonia system, but it was struggling to maintain the store temperature. So the customer thought, I need to add a bit of refrigeration capacity. You can see the plant room down here, a surge drum, a compressor pack, a duo pack with 2 screw compressors, evaporative condenser on the roof of the plant. This ought to be quite a neat, efficient system, and it's serving both chill areas and low temperature areas within the store. The plant was failing to hold temperature. The running costs were very high. The customer felt that he needed a bit more cooling capacity to keep the room down to temperature. So we supplied a package unit, a standalone ammonia package unit, to give 50% more capacity to the chamber. And what we learned was that 50% additional capacity was enough to keep the store temperature down most of the time. Occasionally, the old plant had to kick in and run as well, but for 90% of the year, we ran only on the smaller plant. That doesn't make sense. That really doesn't compute. If the big plant wasn't holding the temperature, the small plant should definitely not be holding the temperature. So there was clearly something wrong with the plant that the customer was generally satisfied with. 7 years later, they came back and we stripped out the old plant and we delivered a second unit, which now enabled them to run the plant on full load without using the old pump system. So what benefits did they get from that? Here you can see the second unit installed beside the first one. No plant room here. This is all outside the building. The only connections inside the building are welded steel pipes to the evaporators. No valves, no flanges, no screwed fittings at all. No chance of ammonia leakage inside the building. So the first unit was installed with no disruption to the plant at all. It was completely independent. We hung evaporators inside the room and we popped the package unit outside. That carried the majority of the cooling requirement and greatly reduced the electrical requirement. The old equipment provided resilience. It was there as backup, but it hardly ever ran. And you can see the second unit also installed with no disruption to the existing plant. It was again a completely independent unit. That allowed us to decant all of the ammonia from the old plant, which was about 1,200 kilograms. And you can see all the barrels arriving on the left-hand side in the truck to take away the recovered ammonia. Each of the new units has a 130 kilogram charge, so we dropped the total charge from 1,200 kilograms to 2 times 130. And the energy use dropped from 36 kilowatt hours per cubic meter to 20 kilowatt hours per cubic meter, so just about half of the consumption previous. That's where it was, and that's where we got it to. So we brought it down, even though the building is old, we brought it down to old best practice. Second case study is a cold store in Scotland. And this one was built in 1971, so the fabric is in very poor condition. And the original refrigeration system, an ammonia system with reciprocating compressors, was in fairly bad shape. The compressors were not efficient, they were not reliable, they had a lot of ammonia leaks, they had a lot of disruption to their operation. We installed 5 packages to this site to replace the old plant. Again, 5 individual modules. You can see 2 down here. These were actually modules that had been supplied to another customer and were then bought back, refurbished, and relocated. 2 chillers. These chillers had originally been supplied to the Welsh Parliament building about 10 years before and had served the air conditioning system. Again, we brought them back, we refurbished them, and we supplied them to this customer as second-hand units. And then to complete the packages, we had to build a new one, which is up the top here. And this one was custom built for the project, but similar style to the other 2 freezer units and to the ones you saw in the previous case study. Now, the benefit of this is it greatly reduced their energy consumption. It reduced their maintenance requirement. Previously, they basically had somebody attending to the plant permanently, and now it's switched to a visit for a day once a month. And they got rid of the water treatment requirements for the evaporative condensers because it's all air-cooled. The system is now more proactive. It predicts performance requirements. It's more responsive, and it adds value to the customer because the investment is not fixed to the building. As I told you, 4 of the 5 units came from somewhere else. This customer, if he decides this 60-year-old building is no longer required, he can take that investment and move it somewhere else. So he has that capital benefit. It's more valuable to him. It reduces the risk of business interruption, it reduces the downtime, and the depreciation is less because the investment is not sunk into the building. So here you can see the 2 second-hand freezer units located outside the building. Same deal, just put them down on the plinth, connect the electrical supply, connect the pipes to the evaporator. So some conclusions. Firstly, extending a building with insufficient capacity can be done without disrupting the plant at all. So the concern that people have that they're not able to cope with the complexity or with the downtime, it doesn't matter. It's not relevant. Adding capacity to an undersized plant, the new plant will take load off the old plant and will achieve the temperature in the freezer and reduce the energy consumption. So it's a triple benefit. If you have a building with a room very far away, for example, a freezer at the end of a long line, and the entire central plant is running at a low suction pressure to serve that one room, putting that one room onto a remote standalone unit will enable an energy benefit in the rest of the system as well. So there's actually a second benefit that can be gained. And if you convert from old ammonia plant to modern ammonia plant, putting the freezer packages close to the evaporators will reduce the suction line losses and improve the efficiency that way as well. The old machinery room, as you saw in the first case study, can then be cleared out and used for some other purpose. So actually they gained valuable real estate on the site as well. They now have a very nice maintenance workshop, which previously was an ammonia plant room. And then if you're converting from old R22 plant or some other CFC or HFC refrigerant, the freezer package can be set to work before the old plant is decommissioned, so there's no disruption to service at all. We've also done this with ice rinks, for example, replacing old R22 chillers with ammonia chillers and keeping the ice on the pad throughout the entire exercise with the switchover. Second conclusions, this leads to lower energy bills, typically less than half the requirement if the store is well run and well maintained. And it could be less than a quarter of the industry average for that given size of store. It lowers the operational cost because the operation is now fully automatic, so there's less need for manual intervention. And it gives secure operation. You can trust that the plant will be operating. Lower risk of disruption because it's automatic, and there's very little chance of any off-site consequence in the event of an ammonia release. And the capital cost investment is spread over many years instead of all being one big hit to replace the central plant, which would be a much more expensive thing to do. So some final conclusions. We can retrofit the package to migrate from R22 without any facility downtime to replace old worn-out ammonia systems, to add to existing systems, either taking off some capacity, as I mentioned, raising the central plant pressure, or boosting the central plant capacity. So how would you do this? Just final slide, some next steps. Firstly, analyze the state, understand exactly what you have, which bits are worth keeping, which bits are good, and which bits desire or require to be replaced. Create a survey and then report back. Look for a prioritized site, look where you get the best return for the investment. Agree on a standard size of unit and roll it out, and then you can move it from one place to another. Get them as soon as you can and then deploy them wherever you can, and maximize the benefit by relocating these units as time goes by to really maximize the return on investment. I hope that's helped understand where we're coming from and what we're looking to do with regard to this new approach to an old technology is the way I would describe it. Thank you very much for your attention.
Thank you very much. Is there any questions? It's on.
It's on.
Ah, yeah, thank you. Thank you very much, Andy. Very interesting presentation and amazing figures, of course. A question is, I'm not so aware of the refurbishment. Is that a common practice in the industry? And how a refurbished system compares with a new system in terms of cost and lifetime? Do you have any ballpark indication?
Oh, no? Yes, thank you. It did not used to be common, but with these packages that can be relocated, we're seeing a greatly growing interest in this, and it's certainly cheaper than buying a new plant. So it's good for the end user, less capital investment. It's good from if you like the term circular economy. The plant that came out from the Parliament building in Wales, for example, would have been scrapped, but we found a second home for it, and it's now 5 years later giving really good service still. So it was certainly not at end of life, and I think that's a really important part of the overall picture as well. In terms of performance, we can refurbish the unit and bring it pretty much back to the as-new performance with a compressor overhaul and cleaning heat exchangers and so on. So there's not really any degradation. Of course, no compressor manufacturer guarantee because the compressor is 10 years old, but that's not been a problem for us.
Thank you. Any other questions? Nope. Either they are sleeping. There's this one here.
Just one question. What about evaporators? I understood that when you are doing this, you are coming with your evaporators, and you could work the system, existing system, while you are installing the new one. And are there possibility to use old evaporator if they could stop with that part of the plant or whatever? So, what is the practice?
It's a really good question, but the low-charge ammonia system requires a very, very specific style of evaporator design. So I would say it's extremely unlikely that the old evaporator would be suitable for that. Not least, it's probably full of oil and underperforming already, but also dirty on the air side. You know, if it's been in service for 50 years, it's not likely to be in good condition. So the cost of attempting to reuse the evaporator would probably be more than the cost of purchasing a new evaporator. And it allows you to do the install without disrupting the old system.
Then probably you're facing the problem of space, because, you know, in the cold store, evaporators take a lot of space. And if you want to put other one in parallel, I suppose that it is much smaller one. And but position and everything else, it could be a problem or not?
Yes, it's potentially difficult in a racked store to find space, and the customer might need to give up some rack positions temporarily, but once we strip out the old evaporators, you can regain positions elsewhere, unless, of course, they're in a pod outside. Every building is different. It needs to be considered specially.
Any others? Nope. Thank you very much. Our next speaker is Jan Boone. A lot of you might know him from many times of appearances at this conference. Jan Boone is from Meyer Carver, Europe. The floor is yours.
Good morning. First of all, thanks, Mr. Chairman, for the introduction, and also to the organization for having invited us to participate in your 55th KGH. Let's say I follow a little bit the points which were highlighted also by Andy. Oh, that's good. Yes, thank you. I have one practical question. How do I use the pointer? Can I use a pointer? What is it? Because it might be more easy, or I must go there with a microphone. I can also go there if you want.
You have the most upper button.
Yes.
You press it. It's going to show like the arrow, if you see. I don't know if the arrow is enough.
I don't see the arrow.
Just a second.
But nothing, let's say, can make a break now. We can start speaking. Let's say, of course, the European market and climate targets to be fully climate neutral by 2050 gives us an important alert that we really have to change and to get rid of the ever chemicals, the PFAS, like we call it. And it's necessary to go for alternatives which help protecting the environment and saving more energy. So following our opinion, the sustainable long-term high temperature, I need to follow with my slide. This is my very old natural 5 matrix, which I show every time, but I like a little bit to highlight historical links to that, because it's all around natural 5 today. Everyone knows natural 5. I would like first to say, you see the first column is ammonia, and I'm happy to say that we are 100 years busy using ammonia and promoting ammonia. It's our 100-year anniversary today, or this year. And the second refrigerant is the CO2. The CO2 application started, in fact, with screw compressors entering the market in '64. And from there we started with CO2 liquefaction plants, but the technology with CO2 is 60 years already available and to be promoted continuously. The third column is the hydrocarbons, which at the same time when the screw started on the market was introduced, mostly at petrochemical plants in the beginning. So these three first columns, they are using oil lubricated compressors, piston and screw. The fourth column, water, do not need a compressor. The compressor is replaced by an adsorber and a desorber. And we use products like, for example, silica gel in the old time. And the last column is air, but it is not normal air compression as we have so many manufacturers available on the market. No, this is special air used as refrigerant, but below minus 50 degrees. And we are using a centrifugal compressor, wall-free, for that job. And it's mostly applied and used in the cryogenic industry. But it is total natural. It's the best natural refrigerant to say. The European market and climate targets, they were highlighted, we mentioned shortly. And in fact, a sustainable, long-term, high-temperature heat pumps strategy lies in the use of available low-pressure compressors technology combined with hydrocarbon refrigerants. The energy demand, which was also already highlighted earlier, shows you that the total energy demand is around 3,000 terawatt-hour per year. And you can see in the green part, that's the 66% is related to process heating. On the second diagram, you can see from the process heating what are the fields of temperature needed. And you will see the top one we don't consider, that's above 500 degrees. We don't consider yet. The yellow one, it is the domain between the 100 and 200 degrees, which is a big part, it's 26%. And there we have challenge. And also on the bottom part, the blue one, below 100 degrees. You can see the fossil, the last column showed the use of which fossil products. In fact, ammonia applications remain valid today and in the future. And our portfolio, in fact, is based on 3 pillars of products. The first pillar, it are standard products available from stock. And I show there the 3 most available at the moment. It is a water chiller, which you see on the top, on the left side, which can produce up to 1,200 kilowatt cooling for water, for example, 12 to 7 degrees water. And it is with a minimum lead time, delivery time available. So you can deliver it, we can deliver it in 1 or 2 weeks. We should always have, the target is to have 20 pieces on stock. It's a FUGU, so-called FUGU unit. It is with a water-cooled condenser. The second unit is also a water chiller, but it is smaller. It is using, or it is installed with an ammonia semi-hermetic piston compressor. and can deliver up to 260 kilowatt cooling, same temperature, the water cooling 12 to 7 or even lower, down to -10 is possible. Here again the same story. Lead time is minimized. Of course, those units have a very compact footprint. They are easily transportable by normal trucks. And there is a very low charge of ammonia in these systems. The TACA, for example, mostly below 30 kilo per unit. And for the top one, it can go up to 60 kilo. Now, the bottom one, we call the M-heat. This is a product which is still, if you consider the technology readiness level of the product, where you have the 3 phases, you have the research, the design, and you have the practical, let's say, application in the field, starting from a labo operation up to a continuous operation. This is a heat pump with ammonia, and it produces 1,500 kilowatt hot water, 90 degrees per hour. And the COP is around factor 5. So we have the case of 1,500 kilowatt output, 90 degrees, and your motor absorbed power will be below 300 kilowatt. And it is the plan to have it available the second half of 2025, also from stock. The unit is very compact. It fits the normal truck sizes, and we can transport 2 skids like that. They are around 6 meters long. 2 skids in a truck, so 3 megawatt. And that's where many users are waiting for, to have a heat pump which can take the heat reacted from, for example, a refrigeration plant or even from a river. That is all what is possible. The second pillar, it are modular spec units. So the unit in the middle, it is using a piston compressor, 66 bar, it's a high pressure. And this unit is a standard modular concept which is adjustable. So the compressor, you see it there in the warm jacket in the front, and you see the complete system, evaporator, condenser, motor, wall system. And the unit is foreseen for also having a suction superheater, a hot gas desuperator, of course the condenser, and a subcooler. So it is complete. And we can adapt, depending on the conditions, we can adapt the heat exchangers and the vessels. So we call it, it's a modular defined unit, and the specs, the specifications can be adapted. It will be always the same outlook of unit like you see it here. The third one, the third pillar, it are customized units. So they are very special, high specification for cascade use, for twin system use, special shape to fit the machine room, out of standard. So these are the 3 basic pillars, which we will take with us also in the next 100 years. And they will also always be a part of the new higher level temperature heat pumps. It's not gone, ammonia stays forever. Now, speaking about the hydrocarbons, of course the benefits of the hydrocarbons is that we have really experience in the oil and gas compressor business, with which we are busy 60 years. And not only we, I speak also for our colleagues. The pressures, they are lower than comparing with ammonia. So it is safety up and cost down. And the oil stability and the choice, of course, is another benefit. The use of screw compressors, of course, there are large MICOM ranges of screw compressors available, and they are easy to operate. the compressor on itself. Then we have higher resistance against fluctuation loads, and we have low toxicity, lower than ammonia. I added here a table in which you can see the operating limits, and you will see that the discharge pressures, they are up to 22 bar gauge. The suction pressures are up to 6 bar gauge. The hot gas temperatures up to 135 degrees for our ranges V and UD. And for our new screw range FC, we go up to 185 degrees with necessary compressor specification adjustments. The oil temperature can be maximum 65 degrees, and the superheat on the discharge side must be bigger than 15 degrees. I show you just for having a more transparent overview. The first column shows you the temperatures, minus 15 to plus 175. The blue column is ammonia. So if you are using, you see there the yellow square, that are our oldest types we have in operation, V-type and UD type. So there we can go up to nearly 22 bar discharge pressure. And if you look to the hydrocarbons, there is the whole list there, from starting with propylene up to pentane. You will see that the pressures under the refrigerant in the column, they are getting much lower. So for operating at 22 bar, it's 55 degrees with ammonia, you come only at a pressure of around 1 bar for pentane, and all in between are following. The J-type is a 30 bar compressor. You can see that in the ammonia column. It is the green square, and you will see that even with pentane, I go to the most extreme hydrocarbon you see here with the lowest pressures, and you see there that we are even not yet at 1 bar. So if we look before, and I speak about the past 100 years, we had, of course, our ammonia applications with our ammonia compressors. You see on the bottom, the J-type series, it is used up to 65 degrees condensing, 67. So it means minus 2, 3 degrees is your water outlet, what you can obtain in that system. Then we have our HK. He is around 85 degrees condensing, and the HS is about 90, 92 degrees. But we want more than the temperature levels you see there. And for the next 100 years, you see on the right-hand side, of course, the ammonias on the bottom, they stay, J, HK, HS, but you will see they are completed with the hydrocarbons. For example, the butane, it can go up to 85 degrees. Then you have the isobutane, there we go over 110 degrees. And then we have the pentane going up to 155 degrees with relative low pressures, which we get in refrigeration for ammonia, but at a much higher temperature. And the capacities you have seen. Now the presentation is around, let's say, we can call it a field case, but it is a special field case because it has been developed as a part of the Spirit Heat project funded by the European Union in collaboration with TNO. It is the Dutch university, technical university for examination, and the European Commission's Horizon Europe program focused on sustainable heat upgrade technologies for industry. The plant which we will have, it is a food processing plant, and it is focused on shrimp cooking by using waste heat from the shrimp freezing plant. So here the Spirit heat program is a high temperature heat pump above 1.2 megawatt by using 145 degrees pentane. The project partners, they are the knowledge provider, of course, that's the university, TNO. The technology provider is us, is Maikawa, and the end user is Stella Polaris. Now, the Stella Polaris, they are producing 15,000 ton shrimps. They are doing the cooking and the peeling of the shrimps, starting from the freezing of the product. So they are using a lot of energy. They are, like you can see here, on the next page is better to see. They use, in the past, they were using the boiler by burning propane. And they needed 9,000 megawatt hour per year to cook the product. So it represented a CO2 emission value of 2,600 tons per year. By applying the heat pump, we can reduce this to 2,000 with 1/4. I'm just taking my slide because I can't go back. By using the heat pump combination, which is in fact a cascade heat pump, because we have the ammonia heat pump, which is kept on the lower temperature, 82 degrees, because of the ammonia and pressure limitation. And we put on a second stage heat pump with pentane, which takes the heat source from the first, or I call it medium temperature heat pump, and pumps it up to 150 degrees. So, in fact, we can summarize what you see here in the table. The energy saving, what is obtained with this concept, is 1,043 megawatt hour per year. And the expected CO2 reduction or savings is 621 ton per year. We have, with this cascade system, a much higher temperature lift because we come from 18 degrees to 140, 145 degrees, so 130 degrees lift. And we have the high temperature operation, which is very attractive for process industries. You can see here a little bit more in detail the ammonia cycle and the pentane cycle. So on the schematic scheme on the right side, you see on the bottom the cooling, the freezing plant. And you see the heat reaction from the freezing plant. Before the heat was rejected, this customer is located in Norway on the west coast. They are neighboring the sea, like we have here the river. And they were giving the heat to the sea, to the environment. You see on the second step, the ammonia medium temperature heat pump, what is pumping up the ammonia from 18 degrees to 82 degrees. These are saturated temperatures. And then we have between the ammonia and the third step, we have the cascade condenser evaporator, which will pump up 78 degrees up to 150 degrees to produce 715 kilowatt, 145 degrees steam at 3.2 bar for the shrimp cookers. So we are using a screw compressor in the pentane unit and the piston compressor like you have seen on the second pillar of our ammonia standardization. So the preheated fresh water is producing finally the steam for semi-continuous or batch operation. This is the reference for the piston compressor ammonia medium heat pump. So you saw it in the first, this is the second pillar of our range. This is a unit which is producing 1,000 kilowatt heating, COP 5.5, and having a charge less than 120 kilo. You see there on the photo, on the right side, you see the compressor, well dressed, if I may say it like that, because we are heating, most of the piping is heated with trace heating. Before we start, we must have everything on a sufficient high temperature in order not to produce liquid by condensation of the ammonia. You can see this is a unit which is fully suited for a suction gas separator, which you see on top above the compressor. Of course, the condenser is in, the evaporator is in. We have the de-superheater of the hot gas, and we have a liquid subcooler in order to be optimal using the liquid temperatures and the gas temperatures to get the best COP out of it. This is also a truck size unit, 2.2 meter wide on 6.3 length. Coming to the hydrocarbon heat pumps, you can see here a simplified scheme from the unit. So on the left side, we have, of course, the heat source in and out from the medium temperature ammonia heat pump coming to the evaporator. And from the evaporator, we are supplying it to the compressor in the middle, which you can see. But before the compressor, you will see there another heat exchanger. This is a superheater, subcooler. We are separating the suction gas with a hot liquid coming back from the condenser. And the compressor is pumping up the energy to 140 degrees. The oil cooler is added to the heat output energy. The cooling is used, so the 65 degrees which we need, because we come from much higher temperature, and is finally added to the heat sink output at the condenser. The top cycle, it is the pentane heat pump. The compressor is a conventional screw, but it's the type FC, and it is oil lubricated. The modifications, because the FC is a little bit modified as the operating regime goes up to 185 degrees, while with normal refrigeration we are staying below 100 degrees most of the time. And the oil system is the bearings, they have a separate closed loop, and the oil is cooled, need cooling, because we must keep the temperature below 65 degrees. We do also degassing of the oil to obtain the best quality for the lubrication of the compressor. We have also the injection oil. This is hot oil, what we are injecting in the machine. And this is a conventional circuit, and that is for optimizing the efficiency of the compressor. Then you see there the temperatures. The heat source of the medium temperature heat pump, 18 degrees ammonia. The heat source of the high temperature heat pump, 78 degrees pentane. Then we have this heat sink on the high temperature heat pump, 150 degrees, 717 kilowatt. And finally the steam output, 145 degrees, 4 bar. So you see a 5 degrees approach on the pentane out and the steam generator. Between the, let's say on the ammonia, you see an approach temperature which is 78 to about 82, if I remember well. Now I added the log pH diagram of the cycle for pentane, because there is an importance. There is a difference with pentane comparing to the normal ammonia systems. normally with ammonia, the compression line following the isentropic curve goes more far away from the gas line, from the coexistence area. The coexistence area, it is the curve going from left bottom up to the right bottom. There you have the two phases. You have liquid and gas. On the complete left side, we are always in the liquid. On the complete right side, we are always in the gas. But the problem we get with pentane, and you see it on the curve which is starting on the bottom at the end of the evaporation, it is going inside the coexistence zone. So that means we are condensing the pentane gas during the compression. And this will result in breaking the compressor, especially the piston compressor. So what we do, we are organizing a safety buffer on superheat. And we try to keep 20 to 30 degrees superheat so that our machine can run always comfortable, will never come in the condensation risk zone. And it makes it very comfortable for part load regimes, load fluctuations, so that's really a must. This is the pentane compressor skid, where you see in front, you see the compressor, again well dressed and heat traced. You see on the right back side the oil separator, and then you see the oil system, the oil pumps, the oil filters as a final skid. So the front skid is the compressor unit. The back skid is the vessel and heat exchanger skid, also containing the steam generator. You can see here, I hope you can read it, you can see here the system design. On the right side you see the machines. The bottom one is the refrigeration unit. In the middle, on the right side, is the medium temperature ammonia heat pump unit. And on the back side is the pentane high temperature heat pump unit. And you can see there the media. So the diagram which you see on the left side, it shows you very clearly the superheater subcooler, which is in the middle, right in the middle of the pentane skid. Now, the temperatures, the media is clear. On the bottom side, we start with the ammonia freezing, -18, and we get the heat source for the medium temperature ammonia heat pump of 18 degrees. And that first ammonia heat pump is pumping up from 18 degrees to 82 degrees. And you can see the capacities. You see the cooling capacity, the heat output, it's 533 kilowatt. The shaft power in the ammonia heat pump is 165 kilowatt. And the COP, just as indication, based on shaft power, is 3.23. This ammonia heat pump delivers output 533 kilowatt heat source to the high temperature heat pump pentane. And you will see it is pumping up from 78 to 150 degrees high temperature pentane. The capacity is 717 kilowatt output with a shaft power 340, COP 2.05. And at the end we have the steam generator on top, delivering us with a 5 degree delta T, 145 degrees steam, which is, I don't see everything so well, but I think it's understandable. Here you see the set. This is a beautiful arrangement. You see the 3 sets. The refrigeration part is not shown, that is on the left side. We didn't add that because that is existing, and that is, let's say, very proven existing technology. So you see there the ammonia heat pump, +18 to +84 on the left side. In the middle, you see the vessel heat exchanger skid with a cascade heat exchanger between ammonia and pentane. Also, the steam generator is in that skid. And on the right side, you see the pentane unit with heat exchangers, vessels, and oil system. Finally, delivering the 145 degrees pentane to make on the middle skid steam generator 100. The 145 is the steam outlet. The pentane outlet is 150 degrees. Now, from the organization, from the spirit heat organization, which is following all the details of the project, we are getting a system coefficient of performance for the different cycles. You have the heating and the COP, that is the combined cycle. In the middle line, you have the heating, and on the bottom line, you have the cooling. And then it is per column, the second column is the cascade heat pump, that's combined total. The middle is the ammonia heat pump, and the right is the pentane heat pump. You see there the 1.78 with a star. So this is the worst case condition when the heat pump is running on the initial design, plus 18, plus 21 heat source for the ammonia heat pump. And the output on the steam side, 145, 150 degrees. If we try to run it at higher source temperature, 22 to 25, and on lower heat sink outlet, 135, 140, the COP can be improved till above 2. You see here our technology readiness level, which is very common to use. We have 3 phases here. Each have 3 lines. The first one is the research on the bottom. The second one is the development, middle, and the top one is the deployment of the implementation of the equipment. So with this unit, the simulation was done by the MyCom W software, and the practical performance is validated, to be validated in pilot projects. We have executed the laboratory test at the university, and today we can say that we are at line 7. The compressor configuration and the heat pump concept is proven in use, but this was only for 500 hours of operation in our factory in Netherlands. So it means if we go to the 8 and the 9, the 8 is implementation with complete system and qualification, and the 9 is operation, is proven operation of in a real plant of preferable 8,000 hours. And then the product is available for commercialization. The next step is we delivered this plant. I call it a plant because it's more than a unit. For regulation also, it is, I must honestly tell you, it is more complex for regulation. You need really engineers following up. It is not just installing, push the button and go home. No, not at all. You will see the commissioning is now, at this moment, busy. So pre-commissioning was foreseen to be ready by end of the year, but it looks like that it will slip into January. And of course, the operational team will follow now and optimize and fine-tune the compressor and the oil system for high temperature operations, and to make it available for the real part load operations and fluctuations we have in the real plant. So our system is not only theoretically and technically sound, but also proven in operational environment, which is crucial for wider adoption in industry. And of course, I are proud to be in the forefront of this change, pushing boundaries of high temperature lift and using pentane as a refrigerant for different heating processes. And as a little present, because this came quite coincidental, I have nice information about the next job we are starting to be delivered end of the year. We have freezing plant, we have cascade units in the freezing plant, and in the heat pump we have also the cascade unit. So globally we have an on top we have a cascade of 2 cascades. It's nice. The bottom, the refrigeration is done with CO2 at -40. And as high stage, we are using the ammonia cooling refrigeration compressor. So we produce -40. We have a capacity heat output of 3.3 megawatt. And the ammonia high stage takes the heat reaction from the CO2, but it takes also users' consumption at 0 and -8 degrees. We have there a total rejection of 5 megawatt. We are not using that all for the heat pumps, but we managed to take with our first stage medium temperature heat pump at 38 degrees the ammonia, and to compress it up to 90 degrees. And we produce there 1.5 megawatt, let's say, heat source, which is then going to the high temperature heat pump, pentane, and it pumps the energy from 90 degrees to 164 degrees. The output is 1,710 kilowatt with absorbed power 820. So we have here again for the pentane side COP shaft-based of 2.09. At the end, the pentane of 164 degrees is used to produce 160 degrees steam. And I forgot to mention the steam quantity, the mass flow in the previous Spirit project was 900 kilo per hour. Here it is 2,500 kilo per hour. And it is a big compressor. The compressor is the size 320. So it's nice. So you can see here the example of a global cascade of 2 cascades. 1 refrigeration, 1 heat pump. It's not so evident to find such a case, but I had it on my desk. But it shows really, really what flexibility you can have. And we are staying within the pressures which we are using many, many years. I speak about 60 years. We are still staying within 23 bar. That's a present. You know, I like to, as usual, I try always to show some. I must stop. The left side is the pentane heat pump. The right is the biogas heat pump. The bottom side is the new heat pump, 1.5 megawatt, which you will have available from end of next year from stock. And the right side is the modular spec heat pump, which you have seen. I like to show you our plant in Smederevo, where we are producing a lot. We are assembling a lot of units. And the last page is our representative in Serbia, which is the company Klima Smederevo. I managed sharp over time, but I think, thanks for your attention.
Thank you, Jan.
Thanks.
Any questions? It seems to be very clear.
Oh, great. Thank you very much.
Here comes a question.
Thank you very much for your presentation. I'm Ryuhei Kaji from Daikin Industries. I have a few questions. One is, do you have any problem for the pentane's heat pump with oil, refrigerant oil? What kind of, like, compared to other, like ammonia, you need like special refrigerant oil or not, I want to know. And then other one is what the purpose to increasing the temperature? Do you see the high temperature is more, like higher temperature is more market, or why you are increasing from the 140 to 160 for the new machines?
The reason is the steam. The biggest industry is steam.
Yes.
The future is if we are able to continue in this industry, our market will be 50 times bigger than what we had in the past. So it is really a very nice present what we get for our next generations.
It's a Christmas present.
Yes, and I do not speak only for us. I speak also for other. And the market will be too big. That's for sure. Every industry, take food, drinks, they all need steam. And with this,
one of the biggest is actually paper industry. They're using a lot at about 150. And paper industry is one of the biggest. Then you have, of course, the petrochemicals. They are also very, very big.
Yes. Yeah. And for your first question, it is a question which I expected to come, but it cannot be disclosed. It's protected by, we have many organizations, the university, the Spirit team, but it's a good question. But I can tell we don't experience problems with the laboratory test, but that's only 500 hours. For me, that's not enough. I like to see 8,000 hours. But it went, but of course, the system, it is more sensible than just a chiller unit, with your control on a setting and it runs. It is a nice tool for engineers. Yeah, and our problem will be maybe lack of engineers in the future, like it is already everywhere in the world.
More questions?
Thank you very much.
Okay, thank you.
Thank you very much.
Thank you for your interest. I hope it was not too quick. All the best. Ah, yes. Great, thanks.
Our next speaker this morning is Klas Berglöf from Klimatskih. Klas has been doing amazing world-beating things with data for literally decades, and he's going to talk to us about predictive maintenance using digital twins. Klas, the floor is yours.
Thank you very much. And let's see this one. Yeah. Okay. So good morning, everybody, and thank you for inviting me to make this presentation. And let's see. Yes, we have my presentation there. So I will talk about something that might scare a big part of the industry. I think it's extremely important that the industry is taking on this with people call AI, machine learning, digital twins. It's going to change the industry, and we heard now that there is a huge opportunity, new technologies. We are moving into new areas where we're producing hotter water, and we see that many systems now are not heat pumps or chillers. They are both. So the complexity is increasing. Also, we hear about the 5 natural refrigerants. All of these are requiring new understanding of the processes. They can be efficient, but I would say that the complexity increase in the world of tomorrow. So we need tools, and that is what we are trying to deal with. So I will skip some of the slides because they are there for information for those. Yeah, I'm much shorter than some other people. Some slides are there for information, and there's plenty of information on the method that we're using, documented in earlier conferences and so on. So there's a lot of public information that you can look up, but there are some indications on it here. So I mean, to put it in the perspective, 20% of the global electricity is used by refrigeration processes. And these are, as Andy showed, they are not well kept. They do not run efficiently. I would claim that there's 10 to 30% energy efficiency gains in average without replacing equipment. And I think that the slide Andy showed also support that. There's huge saving potential by making the system work well. And most failures can be avoided, which is scaring the industry, as the most profitable business is replacing compressors and other components. Most of these can really be avoided. And of course, if you avoid failures, you avoid downtime, loss of goods. 1/3 of the produced groceries are not consumed. And the refrigeration supply chain is a part of that, of course. So there is a lot of pressure on the industry. A lot of focus is on the refrigerants. I do not want to put that down. We need to use new refrigerants that are more environmental, but we cannot continue to not take care of the energy efficiency. So we also know that the climate change by itself is increasing the need for air conditioning and refrigeration. We know that the grids are typically straining to supply the capacity at certain hours. So we need to really use our system to reduce the peak loads. Our systems are generally very slow. There's a lot of inertia in a cold store or in a building, so you might not need to run so much at those specific hours. So there's many challenges, and we need to use the possibilities of AI, machine learning, to do this. I'm a little bit scared of using AI because there's a big reluctance in the building industry because they have been promised so much by AI, and it normally causes more confusion than good results. But we know that the sensors are generally mostly there in the systems, that we need to do a good job. And all buildings today, they use a BMS or BAS system to collect data. And most of them are connected one way or another to the cloud. So everything is there to make a much better job. So I'm not going to go into the details of the internal method. I would say that it's extremely well proven. I patented the method in 1986, but it is basically pure thermodynamics. The only trick is that you need to realize that you can make the compressor a mass flow meter by using the energy law. That if you put energy in, it has to come out. So if you know the entalpies and you know the power that goes into the compressor, do you actually know the mass flow refrigerant? So it's very straightforward. It becomes quite a lot of mathematics and complexity when you have many different systems. I would say that we deal with basically everything today, from industrial, district heating, district cooling, down to small systems. But the beauty is that if we use our thermodynamics, we can calculate all the KPIs of a system in real time. It's all the conventional, of course, superheat, subcooling, and so on. But we can also calculate the energy efficiency on component level. We know the condenser efficiency, the evaporator efficiency, the cycle efficiency, and isentropic compressor efficiency. And then we also know the total efficiency of the system. It's a lot of discussions on COP, but COP is changing with every degree you change your temperature lift. It changes 2 to 5% depending on system and if it's a high side or low side, but it changes a lot. and the systems are very dynamic, and they must be dynamic to be efficient. So if we instead look at the Carnot efficiency at a system working at exactly the conditions that we are operating now, then we can compare with the Carnot COP and the COP that is measured. Then we get an efficiency versus a loss-free process. And we also see at which component is causing the losses. So it becomes a very intuitive way of looking at systems. And then, as Andy mentioned, energy statistics are extremely interesting. And we let the service calculate an energy signature, because if we look at different outdoor temperatures, we can take the statistics at 10 degrees, 11 degrees, and so on. And this means that we can start benchmarking systems that are in different climate zones. And you can, in each system, see if you make a change, did it improve or did it not improve? And you can also monitor what the energy signature that the service built. You can monitor if you deviate from this. So then you have all the performance information on component level, and you have the total outfall, including all these, insulation, if somebody closes the door or not, or whatever. So you have both the total outcome, and you can track the changes. And the German Energy Agency, they identified this with that the industry is not moving. The equipment owners believe that if they cool down, it works. They do not realize the picture that Andy showed, that there is a big difference between what they could do and what they're doing. Of course, this is psychology. The people installing the system think it was good. The people running it think they're doing a good job. So everybody wants it to be good. So they consider it being good as long as it cools down. So to put the pressure on the market, the German Energy Agency wanted to create benchmarks. So we applied, we won the contract to build that platform for them. And then we benchmarked both on a component level, on a unit level, and on energy consumption. And we normalize it, as Andy talked about, the cubic meters. So cold stores, you would normalize on cubic meters, and commercial buildings or supermarkets, you have different normalization factors, square meters or meter display case and so on. You can normalize it on which factors you like. But then you have the energy signature and normalized. That means that you can take buildings of different size in different location, and you can benchmark what they do in a very accurate way. And then we come to automated fault detection and diagnosis, which I think is what's going to change the market. Just to brag a little bit, the National Renewable Energy Laboratory in the US, they made an evaluation of all the automated fault detection and diagnosis system available in the US. And you can see that there are names that are more famous than Klimacheck on the list, but Klimacheck was the only that reached level 3, which means that you identify deviations on component level. So just to give you the saving potential, this is a case done by a large engineering company in the US, where they started to do a pilot on 10 hospitals in Banner Health Group, and they showed a lot of savings. And more interesting, they kept a detailed record on what they have done after recommissioning. When they were monitoring the system for 2 years, they identified 109 issues by performance monitoring. And the interesting thing here is that there are many different things. The chillers are in the middle of a lot of systems, and you need to have all these working well, including the internal controls of the chiller, the BMS controls, and all the supply systems on the outside to have a good systems. But most systems, somebody said before, you push on the button and you leave them, and then everybody's saying it's not my fault, it's somebody else's fault. So you need to monitor, you need to make sure that it works well. And the conclusion also of this project, when they had implemented it on all these 25 hospitals, was that they reduced the maintenance costs drastically. And this is the challenge, because I think that most in the industry would like to do more focus on energy efficiency and reliability, but the equipment owners, they focus on low initial cost. So it's a transition here where you need to pay a little bit more initially to get huge savings on energy and reliability. This is just another case. It's a shopping mall in southern Sweden. They reduced the energy consumption for air conditioning to 50% with the same hardware. This was how it was controlled before and after. And this chiller supplier, we see the same problems on most of the systems that they deliver. The controller is very tricky to set correct, and nobody's doing it. They always blame the building for the problems. When you start pushing it, you can get it to work well. And then they did this recommissioning of the controls, getting system to work, fixing a number of different issues out in the system. Then there was detected a deviation on condenser efficiency. So the condenser was fouling, and they cleaned it, and that saved 7.5% and avoided a lot of, there was no downtime except for the planned activity, which when they run another chiller. And you can say that they reduced 90% of the call-outs of the technicians during these the time after the improvements. Here is just another example. This is a beautiful system with variable speed drive compressors and so on, and it's just not well commissioned, and nobody would do anything in spite of that we complained until they had 2 compressor failures. We see way too many compressor failures with variable speed drives because of that they are not commissioning the system correctly. Peak load, this is going to be a major opportunity for the equipment owners and for the industry. This was done on an IKEA store on the commercial refrigeration in an IKEA mall, and they reduced the peak load during between 8 and 12 in the morning, when there was we had a peak load in the grid, to 50%. And as a side result, they saved 20% of the energy consumption because they were running more at night when it's cooler outside. So in spite of running colder on the display cases and cold rooms, they also were having a lower pressure ratio. So there's a lot of different issues. You have it in the list. But the solution then will be the digital twins. We can detect any performance deviations, but it requires engineering hours. And for hundreds of millions of systems, there's not enough engineers. So it means that you need to use the tools. We have done 2 master theses showing the efficiency of the digital twins, and we are now in a project with enhancing and expanding this to more features. But this picture shows that blue is a measured performance of one system, and the yellow is what the digital twin predict. So you can see it's extremely close. And this is not the same system. This is the same design, but it's 2 different systems. And you get very close to the prediction. And this shows subcool, which is an indicator in many systems for refrigerant charge. And you can see that there is a challenge for engineers to know if it should be 4. Sorry, I've got some time. Okay. This didn't work well. Yeah, so apologize for this. Yeah, so indirect leak detection is extremely efficient. You can detect leaks because they changed the operational system, but subcool is a good indicator, but it varies naturally of operating condition. So if the digital twin tells you what it should be at these conditions, you can work much more efficiently. This is showing compressor efficiency. There are thousands of compressors killed every year on this problem, where you get liquid carryover from either, these are tandem scrolls, and it leaks backwards through the standstill compressor, or you can have expansion device issues causing that you get liquid return or excess oil transport, and you cool down the compressor. You see it immediately if you monitor it, and you can save the compressors. It's thousands of compressors destroyed every year on this. And this is showing, the blue one is the installed system, and the yellow one would be what happened if you run it on a competitive design. So there is a difference between a system efficiency index of 30 roughly to 43. So if you had bought the yellow one, you would have used 50% less energy on 2 competing bids for the same site. Data is there. Data just can be moved to servers and analyzed. There are many ways of doing that, but it can be done cost effectively. So this is going to change the whole industry. We will have people working with taking the analytical results, and you will have people correcting the issues. You will not need to go to the site to troubleshoot, because you will know why you go there. Send the right person out, and before it fails, you fix the problems. So that was a quick introduction to what you have to expect.
Thank you very much, Klas. Do we have any questions from the audience? Yes.
My question is regarding that IKEA case. You succeeded to save 20% or something like this with shifting cooling during the night. So could you elaborate it much more, because I don't understand what has happened. If you need cooling during the day, how you could shift it during the night? Do you have some thermal storage or whatever? Thank you.
No, I mean the goods is very heavy. A building is very heavy. So if I overcool in the night, so I lower the temperature with a couple of degrees, and then I run my refrigeration system. Maybe I allow, depending on, you control it depending on what the actual need is. But if you maybe need 60, 70%, you only allow 30% of the capacity. Then you get the situation where your evaporation temperature will increase slightly, but because it's increasing, you get more capacity. And it takes a very long time for the goods in the freezers to slide. So you cool them a little bit, and then you maintain a base load, and then you allow them to slide, but not outside of the regulations. So you keep them within the...
So you're using inertia, so it's...
Exactly, exactly.
It's well known, but it means that you're cooling during the night something lower which you don't need. So you're using electricity to cool lower than needed. But okay, at the end it's 20% when you...
Yeah, I save 20% of energy. I buy electricity at night, maybe for 10% of what I would do during the peak hours. I get lower tariffs because I have lower peak load. So this is going to be something you need to learn. I just promise you it. You have to use system inertia.
Any more questions? Okay, well, Klas, thank you very much. Really interesting presentation covering a huge amount of different subjects, so thank you. Oh, Klas.
I have it. nastavljamo dalje. Gospodin Đurović me je zamolio da ga prebacim ranije, međutim, koliko ja vidim, on je morao da ode zbog toga što imao neke obaveze, pa onda nastavljamo po ovom standardnom programu. Imamo predavače iz firme Danfoss, gospodin Pavle Babić će da prezentuje rad, ali autori su, pored njega, Vladimir Beljanski i gospodin Angolani. Tema je smanjenje punjenja amonijačnih rastlinnih sistema i povećanje energetske efikasnosti Danfoss Neo Charge.
Just first, one short information. I will be the first speaker to address presentation in Serbian language, so for non-Serbian speakers, the headsets are available in front. Dobar dan svima. Pre svega da izrazim jedno lično zadovoljstvo što mogu da se obratim pred svima vama koji ste doprineli razvoju naše industrije, ali i obrazovanju kadrova koji rade u industriji. Moje zadovoljstvo je toliko veće što ću pričati na temu koja je premijerno predstavljena na sajmu Chillventa u Nemačkoj pre 2 meseca. Tiče se smanjenja punjenja amonijačnih sistema i povećanje njihove energetske efikasnosti. Ok. Pre svega, zbog čega ovo pričam? Amonijak, rastlini fluid koji je nama dobro poznat, ali ajde da se podsjetimo zbog čega ovo sve radimo. Amonijak je stari rastlini fluid koji je spreman za budućnost, ima fenomenalne termodinamičke karakteristike, nulti potencijal globalnog zagrevanja i nulti potencijal razgradnje ozona u atmosferskom omotaču. Međutim, postoje i one njegove manje popularne stvari, to je toksični rastlini fluid i zapaljiv. Pripada grupi rastlinih fluida B2L. Postoji trend koji omogućava, da kažemo, postojanje sistema sa niskim punjenjem amonijaka. To su pre svega, da kažemo, ovo što sam naveo, da želimo da ga koristimo jer je efikasan i prirodno rastlino sredstvo, ali imamo i sve veći fokus na povećanju bezbednosti ovakvih sistema, s obzirom da imaju velika punjenja i želimo da smanjimo rizik od curenja kod takvih instalacija i da budemo svesni da kod nas to još nije stiglo, ali u Evropi postoje mnogi lokalni pravilnici i zakonskom regulativom je tačno uređeno koliko je dozvoljeno punjenje sistema u urbanim sredinama. Jedan kolega iz Danfossa, Thomas Lud, je uradio studiju slučajeva gde je poredio različite tipove sistema i potrošnju energije. Postoje 2 tipa sistema koje u studiji slučaja obradio i njihove rezultate sam ja predstavio na ovim slajdovima. To su direktni sistemi koji se drže samo primarni rastlini fluid u krugu i oni sistemi koji imaju i primarni i sekundarni rastlini fluid u krugu. Studija slučaja rađena je takva da su sve instalacije u istim uslovima simulirane, one su u centralnoj Evropi, isti uslovi rada su na isparivaču, kondenzatoru i pad temperature na izmenjivačima je usvojen da je isti. Kao rezultati studija slučaja dvostepeni amonijačni sistem je daleko najefikasniji. Pored toga imamo direktni sistem sa azotropskom smešom, takođe dvostepeni, koji ima nešto veću potrošnju energije i imamo kaskadni sistem amonijak CO2 koji takođe u ovoj studiji slučajeva ima veću potrošnju energije, a objasniću kasnije zašto u odnosu na dvostepeni amonijačni sistem. Sekundarni sistemi koji imaju sekundarni rastlini fluid, odnosno bilo to da je neki utašnjeni CO2 u sekundarnom strujnom krugu ili mešavina propilen glikola, imaju daleko veću potrošnju električne energije zbog toga što imaju temperatursku razliku i na izmenjivačima toplote, ali i potrošnju energije za pogon cirkulacionih pumpi. Međutim, sa uvođenjem sekundarnog rashladnog fluida u ceo sistem mi smo uspeli da smanjimo količinu punjenja u primarnom rashladnom krugu, tako da zaključak je da iako smo smanjili količinu punjenja u primarnom rashladnom fluidu, mi imamo u primarnom rashladnom krugu, mi imamo manje efikasan sistem. Tako da moramo da poradimo na tome da direktni sistemi koji imaju samo primarni rashladni fluid imaju smanjeno punjenje. Da li to možemo da uradimo? Da, jedno od rešenja je i Danfoss Neo Charge. Ovde je prikazan grafik gde možemo da vidimo efikasnost u zavisnosti od temperature i isparavanja. Efikasnost amonijačnih sistema je prikazan crvenom linijom i on je, da kažemo, konstantno efikasan. Zelenom linijom je prikazan kaskadni sistem amonijak CO2 i tu vidimo da njegova efikasnost je veća od amonijačnog sistema isključivo na temperaturama isparavanja ispod minus 30 stepeni, dok sistemi koji imaju sekundarni rashladni fluid poput propilen glikola imaju permanentan pad efikasnosti sa snižavanjem temperature isparavanja. Postoje dve vrste sistema koje možemo sresti kod amonijačnih instalacija na čiji rad možemo da utičemo. Jedna vrsta sistema su pumpni sistemi sa isparivačima koji imaju recirkulaciju i mi sa ovim tehničkim rešenjem utičemo na smanjenje koncentracije amonijaka u sistemu za nekih 40 do 50% i postoje, da kažemo, amonijačni sistemi sa direktnom ekspanzijom koji imaju već tradicionalno nisko punjenje. Mi sa ovim tehničkim rešenjem ne možemo dodatno da umanjimo njegovo punjenje, ali možemo da utičemo na efikasnost razmene toplote. Koncept ovog tehničkog rešenja je da se sastoji iz neke paketne opreme. Pre svega tu je namenski razvijen upravljač EK 450 koji ima patentirani algoritam za ovakvu aplikaciju. Postoji grupa senzora od kojih su dva, da kažemo, konvencionalna standardna senzora. Jedan je senzor temperature, drugi je senzor pritiska i specijalni namenski senzor sa termičkim elementom u sebi, neosenzor koji, da kažemo, sva ova tri senzora daju informacije kontroleru koji nakon obrade informacije govori o stanju pare, odnosno pregrejanog gasa na izlazu izmenjivača, bilo da je slučaj direktne ekspanzije ili želimo da smanjimo količinu punjenja u sistemu. I naravno, za sve to potreban je jedan izvršni organ, to je regulacioni ventil koji može biti pulsnog ili modulacionog tipa. Kako se posmatra potencijal smanjenja količine punjenja u ovakvim sistemima? Nekada razvijeni sistemi su projektovani sa višim vrednostima cirkulacionog broja, naravno sa razvojem elektronike, automatike, izvršnih organa u automatizaciji rashladnih sistema. Mi danas projektujemo sa nešto nižim vrednostima nego što se to radilo pre 40-50 godina. Međutim, tehničko rešenje Danfoss Neo Charge daje novi potencijal za smanjenje u retrofitu postojećih instalacija. Još veće smanjenje punjenja može da se uradi ukoliko se radi novo projektovana instalacija, ali sa konceptom Neo Charge. Objasnit ću u narednim slajdovima i gde se to odražava. I najveći potencijal za uštedu je da se napravi DX amonijačna instalacija, znači sa direktnom ekspanzijom uz pomoć ovog tehničkog rešenja. Kontrola sistema sa niskim punjenjem. Tokom ove prezentacije obradit ćemo primjenu Neo Charge rešenja kod isparivača sa recirkulacijom amonijaka, kao i kod isparivača sa direktnom ekspanzijom. Međutim, za početak da objasnimo princip rada neocharge rešenja. Svima nam je poznat logaritam pH dijagram i oblast rada kod tradicionalnih pumpnih sistema. Mi na izlazu iz isparivača imamo vlažnu paru koja u zavisnosti od cirkulacionog broja može da ima vrednost od 0,3 do 0,5 i ona je na prezentaciji obeležena ovim brojem 4, to je područje rada. Primjenom tehničkog rešenja Danfoss neocharge i uticajem na regulaciju cirkulacionog broja, mi pokušavamo da dovedemo stanje pare blisko suvo zasićenoj liniji koja je obeležena pozicijom 2 i da ima, da kažemo, vrednost od 0,9. U slučaju kontrole pregrevanja kod sistema koji imaju direktnu ekspanziju, znači postoji, tu već imamo tradicionalno nisko punjenje, ne utičemo na smanjenje količine punjenja, ali povećavamo efikasnost rada samog isparivača, tako što sa neocharge tehničkim rešenjem utičemo na smanjenje pregrevanja na kraju isparivača, da iz područja pregrejanja pare dođemo do linije zasićenja i da pregrevanje bude približno 0 Kelvina, odnosno da budemo u onoj granici minimalnog stabilnog pregrevanja. Ovdje je prikazani model neosenzora koji je, da kažemo, jedna od specifičnosti ovog rešenja. To je senzor sa termičkim elementom. On je na legajućeg tipa, znači nema potrebe da se dodatno obrađuje cev isparivača, da se buši, postavlja čaura i postavlja uranski senzor. On je potpuno, da kažemo, van uticaja unutrašnje struje i vrlo je specifičnog dizajna kao neki revolver, što mu daje određenu fleksibilnost. Svaka pozicija ovog senzora ima drugačiji radijus, tako da pokriva više standardnih cevi koje se može naći u izradi isparivača. Inače, ovaj senzor koji nam govori o kvalitetu pare ili gasa na izlazu iz izmenjivača. Malo detaljnije o isparivačima sa recirkulacijom amonijaka, odnosno kod pumpnih sistema. Na ovom slajdu je prikazan potencijal smanjenja količine punjenja u pumpnom sistemu i primjer je dat na sistemu kapaciteta 1 MW u temperaturskom režimu rada od -30 do +30. Sa plavim stubovima je prikazana količina punjenja amonijaka u kilogramima ukoliko je cirkulacioni broj 3 i ukoliko uzmemo da kontrolišemo cirkulacioni broj uz pomoć neocharge-a i dovedemo ga da on u režimima rada bude 1,1, to predstavlja crvene stubove. Kao što vidite, razlika postoji isključivo u niskom pritisku, odnosno delu sistema koji je od sistemskog separatora, svi tečni vodovi, svi izmenjivači i povratak vlažne pare do sistemskog separatora. Uticaj na količinu punjenja amonijaka na strani visokog pritiska nema uticaja. Zbog čega ovo radimo? Pa imamo, da kažemo, konvencijalni sistem gdje imamo regulacione ventile koje služe u svrhu nekog hidroličkog balansiranja potrošača i sve to pretpodešavamo za projektne uslove. Međutim, projektni uslovi nisu permanentni u toku rada sistema, vrlo često imamo i parcijalno opterećenje i u parcijalnom opterećenju imamo, da kažemo, situaciju gde usled nekontrole cirkulacionog broja on može višestruko da poraste. Na ovom grafu je prikazan porast cirkulacionog broja sa padom opterećenja za, da kažemo, početnu vrednost cirkulacionog broja 3, on i višestruko može da poraste preko broja 6. Ukoliko kontrolišemo cirkulacioni broj uz pomoć neo-charge tehničkog rešenja, mi se trudimo da on bude između 1 i 2 i to uspevamo da održavamo i u parcijalnom opterećenju, naravno uz adekvatno dimenzionisanje ventila. Što se tiče posledica korišćenja ovoga, mi imamo situaciju da potrošnja energije opada, jer, da kažemo, manje pogonimo pumpe i možemo da čak dimenzionišemo i manje kompresore, ukoliko se pitamo o novo projektovanoj instalaciji. Primjena ovog koncepta, kao što sam rekao, efikasnost ostaje jednako dobra kao i kod tradicionalnog pumpnog sistema. Jedino što utičemo je na smanjenje količine punjenja, o zavisnosti od slučaja do slučaja i do 50%. Kako to zapravo izgleda u praksi? Prikazan je jedan isparivač sa napajanjem sa donje strane, gde kontrolišemo cirkulacioni broj kod pumpnog sistema i ono što je bitno da napomenem, ovo tehničko rešenje ne kontroliše cirkulaciju kroz svaki strujni krug isparivača, već vrši kontrolu na nivou srednje vrednosti za ceo isparivač. Recimo da je ovde srednja vrednost cirkulacionog broja 1,5. U ovom slučaju sa HS smo obeležili poziciju gde ćemo postaviti neosenzor, to je senzor sa grejnim elementom i kao što možete da vidite, to je najopterećeniji strujni krug u isparivaču. To je prvi strujni krug u struji vazduha. Odmah na sledeći strujni krug mi postavljamo temperaturski senzor i posle zajedničkog kolektora senzor pritiska. Sve ove 3 informacije se obrađuju u namenskom upravljaču i daju nam informaciju o stanju vlažne pare i njenom kvalitetu na izlazu iz isparivača. Gde je potencijal ovog koncepta? Pa, najveći je potencijal tamo gde imamo postojeći sistem, imamo potrebu da proširimo kapacitete, međutim, ograničeni smo fizičkim prostorom u mašinskoj sali, nemamo mesta za novi separator, za novu opremu. Mi sa postojećim količinom punjenja možemo da uradimo retrofit postojećih potrošača ili novoplanirane potrošače da svedemo na koncept neo-charge kontrole recirkulacije, tako da praktično sa istim punjenjem u mašinskoj sali možemo da dobijemo veće kapacitete, a da ne utičemo na smanjenje energetske efikasnosti, tako što smo uveli neki izmenjivač i sekundarni strujni krug, pa imamo pad temperature i na tom izmenjivaču, ali i trošimo dodatnu energiju za pogon cirkulacionih pumpi. Ovde je jedan slajd napravljen sa rekapitulacijom priče na ovu temu. Zbog vremena ja ću samo da prođem preko njega. Što se tiče isparivača sa direktnom ekspanzijom, koncept neo-charge-a i direktne ekspanzije je vrlo sličan. U slučaju kontrole direktne ekspanzije mi imamo tu klasično senzor pritiska, senzor temperature i ekspanzioni ventil, tako, i neki standardni upravljač pregrevanja koji na osnovu informacije o temperaturi i pritisku zna koliko je pregrevanje na izlazu iz isparivača. Ono što omogućava da sistem bezbedno funkcioniše je minimalno stabilno pregrevanje. To je situacija kada više ne postoji tečne faze unutar gasa. Naravno, sa pregrevanjem mi imamo i situaciju da temperatura isparavanja treba da bude nešto niža kako bi se i ona kompenzovala. U slučaju primjene NeoCharge tehničkog rešenja, tu imamo dodatno i neosenzor koji smo malo pre spomenuli sa grejnim elementom i tendencija je da smanjimo pregrevanje na 0 Kelvina i da ga dovedemo do suvozaštićene linije u oblasti rada. Ukoliko primenimo ovaj koncept, mi dodatno ne snižavamo količinu punjenja, jer su sistemi sa direktnom ekspanzijom sistemi sa tradicionalno niskim punjenjem. Međutim, povećavamo efikasnost, s tim što treba obratiti pažnju da sa željom da povećamo efikasnost mi možemo da za bolji rad isparivača i uđemo u područje vlažne pare namerno, tako da je neophodno obezbediti usisni akumulator kako bi zaštitili i kompresore od tečnih udara. Kako to u praksi funkcioniše? Ovaj upravljač inicijalno krene da radi kao da ima DX kontrolu sa pregrevanjem i tek kada uđe u stacionarne neke režime rada, dođe do zaključka da treba da ima tendenciju da obori temperaturu pregrevanja. Tako da ovde imamo, da kažemo, početne uslove rada gde se ventil, da kažemo, upravlja tako da ima pregrevanje, crvenom linijom je obeleženo pregrevanje, ima pregrevanje u zavisnosti, vidite da je promenljivo od 0 do 15 stepeni. Kada upravljač skapira da već ima repeticiju nekog rada što se tiče ventila i došao u stacionarne uslove, onda kreću tendenciju da obara pregrevanje, da bude vrednost pregrevanja bliska 0 stepeni, a samim tim imam i pomeranje temperature isparavanja na viši temperaturski nivo. Za razliku od malo pre pomenutog pumpnog sistema, što se tiče direktne ekspanzije, tu je logika postavljanja ovog senzora drugačija. Senzor sa grejnim elementom se postavlja na najmanje opterećeni strujni krug isparivača, to je uglavnom onaj poslednji po struji vazduha, dok se senzor temperature i pritiska postavljaju na zajedničkoj liniji iza samog kolektora. I za kraj sve ovo radimo za neki novac, tako da bitno je prikazati investicioni aspekt. Što se tiče tradicionalnog sistema i ovog NeoCharge principa, investicija je reda veličine ista, međutim, distribucija troškova je drugačija. Zbog smanjenja, da kažemo, količine punjenja amonijaka mi možemo da dimenzionišemo manje sudove, manje cevne vodove, manje pumpe i manje je potrebno mesta za instaliranje ove opreme, kao što će se odraziti na nižu cenu glavnih komponenti cevovoda, ali da kažemo sama armatura je nešto skuplja nego tradicionalna. To bi bilo ukratko od Amfos NeoCharge. Vidim da gospodin Đinić ima pitanje.
Hvala kolega Pavle.
Hvala kolega Beljanski. Ja imam jedno pitanje. Vi ste u vašem radu tretirali samo isparivač kao komponentu rashladnog sistema koji i uspjeli ste sa analizom u stvari pregrevanja iz isparivača da dobijete 40% uštede, odnosno smanjenje punjenja sa amonijakom. Sad ja vas nešto pitam, da li postoji još neke komponente u tom sistemu na koje možete da utičete da dopunski smanjite punjenje amonijačnih sistema, pogotovo kad su u pitanju, recimo, čileri sa vazduhom hlađenim kondenzatorom?
To je tendencija sledećeg razvoja ovog neocharge-a, pogotovo kod chillera. Pre svega, ovo je sada predstavljeno rešenje za neke stacionarne uslove hlađenja kao što imamo kod komora. Što se tiče chillera sa vazduhom hlađenim kondenzatorom, tu već imamo situaciju da, ne znam, imamo uticaj vetrova i trenutno se i radi na dodatnom razvoju i ispitivanju za takve aplikacije.
Pa ste, impozantno je smanjenje 40% samo sa pregrevanjem. Mislim, to je prosto, pravo da kažem, malo i neverovatno, ali ja se nadam da ste to uspeli i da izmerite negde.
S obzirom da je to predstavljeno u oktobru ove godine, prethodne 2 godine su mnogi pilot projekti urađeni širom sveta. Sad, to je ono kad kažemo širom sveta, to je tamo negde urađeno, ali evo, ja sa zadovoljstvom mogu da kažem da Danfoss sa lokalnim partnerom razvija jedan prvi projekat koji se izvodi u Hrvatskoj i bit će pušten sledećeg januara u pogon.
Dajte to i kod nas da uradimo.
Ja samo tražim dobrog partnera, evo, uradit ćemo. I dobrog investitora da to podnese.
To je najhvalje. Hvala najlepše.
Hvala vama.
Ja bih imao neka pitanja. Prvo, imamo 3 senzora, znači temperaturski senzor, senzor pritiska i neosenzor. Meni i dalje nije jasno kako funkcioniše neosenzor. Mislim, to je ključno, da kažem, to je ključna stvar.
Ovo je inače druga verzija prezentacije koju sam pripremio. Prva prezentacija je sadržala i matematički model za koju sam dobio sugestiju da ne bi trebao da prikažem još uvek jer otkriva algoritam rada. Neosenzor indirektno određuje kvalitet gasa ili pare na samom izlazu. A princip njegovog rada je da termodinamičke karakteristike vlažne pare i pregrejanog gasa nisu iste.
To je tačno, ali u celoj priči, ako imamo preplavljen isparivač ili ako imamo direktnu ekspanziju, to je znači sadržaj pare na izlazu iz isparivača. Mi ne možemo da isti isparivač koji je prepravljen i koji ima koeficijent punjenja 4 ili 6, da koristimo za direktnu ekspanziju, zato što on će biti mali. Neće dati taj efekat. Kako ćemo mi da po vašoj prezentaciji ispada da mi povećavamo efikasnost sa smanjenjem punjenja, a smanjenje punjenja praktično po termodinamici samo po sebi smanjuje efikasnost isparivača. Najefikasniji isparivač koji ima najmanje pare na izlazu.
Možda ja nisam bio dovoljno jasan. U slučaju pumpnog sistema, da imamo kontrolu cirkulacionog broja, mi tu samo utičemo na smanjenje količine punjenja. Ne pravimo efikasniji sistem. Efikasniji sistem je u slučaju direktne ekspanzije. Znači, ako imamo postojeći sistem amonijačni sa direktnom ekspanzijom, mi možemo da uradimo retrofit takvog sistema ili da uradimo novi sistem, gde ćemo smanjiti pregrevanje i napraviti efikasniju razmenu toplote. Više nećemo imati, da kažemo, onaj deo isparivača koji neće imati utilizaciju zbog pregrevanja.
To je logično, ali onda dolazimo u opasnost da dobijemo tečni udar na kompresoru. Znači, onda treba se napravi zaštita od tečnog udara.
I zbog toga sam i u šemi prikazao i napomenuo da je neophodno obezbediti usisni akumulator kako bi zaštitili mašinu od tečnog udara.
Hvala vam.
Mene zanima samo taj senzor, rekli ste da je sa grejačem. Čemu mu služi taj grejač?
Pa...
Samo da kažem u ime Danfosa da nama nije dozvoljeno da pričamo o toj tehnologiji, jer postoje 3 patenta i neki patenti čak ne smemo ni njihove brojeve da delimo, zato što je to pod velikim velom zaštite kako se radi. Taj senzor služi da nam pokaže da li je isparivač u kom je režimu, da li ima višak ili manjak amonijaka. Toliko je ono što možemo da kažemo. Znači, ne možemo da dobijemo tačan broj, to je toliko %, nego da li je potopljen ili nije. To je najviše što možemo da kažemo. A sve nas zanima kako radi senzor, jer je matematika iza toga jako dobra. Imamo patent na softveru i poenta je da mi ne prodajemo komponente, znači kupite senzor, neće vam značiti ništa, nego kontroler sa svim uređajima koji ga prate, znači sa svim ovim senzorima. Senzor je samo izvršni element, prava logika unutar kontrolera koji nam pokazuje šta i kako. I dodao bi samo za ovu efikasnost kod prepravljenih sistema da postoji mogućnost i tu da smanjimo, jer pad pritiska u usisnoj grani u rajzeru je manje ako imamo cirkulacioni broj 1, nego ako imamo 4, zato što manju količinu tečnosti dižemo. Koliko zavisi od instalacije do instalacije, da li je kraća ili duža, koliki je rajzer. Ali merenja su pokazala da to radimo. Čisto imamo preko 30 pilota gde su se ovo što smo pričali pokazali. Neko je koristio za tunere da bi snizio tačku isparavanja baš zbog pada pritiska u rajzeru i onda kompresor je dobio Kelvin do 2 da može raditi na višem isparenju. Neko ima problem sa zakonom pa kaže želim da proširim instalaciju, da zadržim isto punjenje i onda to je drugi razlog iz koga koriste. Treći je kada žele da prošire instalaciju, onda zadrže istu količinu amonijaka i rade ekstenziju sa postojećim količinom. A sva pitanja za senzor, nažalost, ne možemo da vam damo odgovor u ovom trenutku, možda za nekom drugom periodu.
Ali znamo.
Ali znamo jako dobro.
Zahvaljujem se. Znači, samo jedna konstatacija da senzor praktično treba da kontroliše, ako ja dobro razumem, kontroliše količinu pare koja izlazi iz isparivača i na taj način upravlja radom celog sistema. To je to. Vreme nam ističe, plašim se... Izvolite.
Samo kratko. Ja samo da napomenem mojim kolegama da sam pre 20 godina tačno u Dijamantu ugradio amonijačni sistem sa direktnom ekspanzijom, ali je sreća moja što sam bio oprezan pa sam ugradio akumulator pre kompresora, tako da nam se dešavalo da više puta da potopimo taj isparivač gde smo ugradili vaš onaj 38E ventil koji kad dođe dosta onda puštamo topli gas i ispraznimo taj amonijak i idemo dalje. Ali je neophodno da se ima taj akumulator kod direktne ekspanzije, jer dovoljno je da zakaže bilo koji ventil u sistemu i da potopite kompresora, a znamo da su pogotovo klipni kompresori vrlo osetljivi na tečne udare. I moje jedno pitanje je samo da li razmišljate o početku proizvodnje sistema za zaštitu svih tečnih linija, od resivera pa nadalje, separatora, pumpi, potopljenih pločastih razmjevača toplote i tako dalje, da u slučaju akcidenta kad detektor amonijaka pokaže određenu vrednost, da mi zaustavljamo, prekidamo isticanje amonijaka u maškoj sali ili tamo gde već postoji.
Hvala, gospodine Žikice. Da, to je u agendi našeg razvoja, međutim, tu postoji, da kažemo, i uglavnom zahtev da pogon takvih ventila bude nezavistan i uglavnom je pneumatski. To je nešto u Danfosu još uvek nema u svom proizvodnom programu, ali svako se ide ka tome.
Hvala gospodine Babiću. Bilo je interesantna prezentacija i bilo bi još mnogo pitanja, pretpostavljam, ali pošto je ovo nova stvar, bit će u buduće i nadam se da ćemo i na sledećem kongresu imati nastavak priče o ovoj temi. Sledeća prezentacija je, prezentaciju će da nam izloži gospodin Krapanić, koji je dugo godina naš drug i kolega i koji dolazi iz Hrvatske i koji je imao do sada mnogo lepih prezentacija. Tema je toplotne pumpe u EPBD-u, prilike i izazovi. Izvolite, gospodine Krapanić.
Hvala lijepa, Slobodane. Koristim ovu priliku da vas pozdravim, ali isto tako da zahvalim organizatoru što je omogućio i prepoznao da je ova tema interesantna dovoljno da bude dio ovoga kongresa i jako mi je drago da evo već 8 godina od kad sam u Hrvatskoj dolazim ovdje redovito. Kad se spomene EPBD kao direktiva o energetskoj efikasnosti u zgradama ili energetskim svojstvima zgrada, ako razgovarate sa ljudima iz ministarstava, svi se hvataju za glavu i kaže to je nemoguće, to je preambiciozno, a završava sa jednom najljepšom rečenicom ko će sve to platiti. Ova prezentacija naravno ne može dati odgovor na tako nešto, ali ja ću probati u stvari dati nekakav pregled kako to izgleda vezano za našu industriju, isto tako možda više orijentirano na nekakav sektor gdje borave ljudi, odnosno u zgradama i kućama gdje borave ljudi. Ovo je meni jedan od najdražih slajdova, u stvari najdražih prikaza koji je Eurostat redovito obnavlja, koji nam pokazuje u stvari onu nekakvu najmanju cjelinu, a to je kućanstvo, koliko se energije troši u kućanstvu i kako. I ovdje je standardno da oko 80% ukupne energije u jednom kućanstvu trošimo na grijanje i potrošnu toplu vodu, odnosno za grijanje vode. Naravno, ostatak je za druge potrebe kao što su kuhanje, osvjetljenje i tako dalje. Sad, tu toplinsku energiju koja nam je potrebna za grijanje i grijanje tople vode u stvari dobivamo na nekoliko načina. Kakve imamo mogućnosti? Direktno preko daljinskih grijanja transformiramo ih iz nekih drugih izvora energije koji mogu biti fosilni, mogu biti čisti, izvori energije, može biti električna energija koja daje impuls, koja opet ima svoje načine proizvodnje, mogu biti i obnovljivi izvori energije, djelomično, što je toplotna pumpa, odnosno dizalica topline, jedan dobar primjer. Što se tiče biomase i drva, to za jednu drugu diskusiju, meni to, ja nikako se ne mogu kao inženjer, ne mogu se složiti da je to obnovljivi izvor energije, ali za sada je to još uvijek dio nekako regulative. I sad ono što nam je u cijelom tom procesu jako bitno, što je gospodin Pearson jučer spomenuo, je elektrifikacija, u stvari elektrifikacija svega, odnosno većine, kako bismo u stvari smanjili ovisnost o nekakvim različitim izvorima energije. I ono što nam je ovdje bitno, da elektrificiramo grijanje, odnosno pređemo na jedan izvor energije koji u stvari možemo i sami proizvesti. I to je onda ta nekakva elektrifikacija grijanja, gdje i onako do našeg kućanstva dovodimo nekakvu struju, nekakvu električnu energiju i onda tu jednu električnu energiju koristimo za sve potrebe u jednom kućanstvu. Znači, prvi korak elektrifikacija nekakva. Skrenut ću malo sa ovoga, jer energija, kako izgleda energetska slika danas u Europi. Europa sama proizvodi tek 1/3, nešto malo više od 1/3 energije koja je potrebna, odnosno govorimo o svim energentima, a uvozimo oko 63%. Ako pogledamo tu vlastitu proizvodnju, ona stvarno izgleda jako, jako dobro. I sad bi čovjek pomislio, situacija je stvarno, ide u jako dobrom smjeru, već smo jako puno napravili, međutim nismo, jer ne smijemo zaboraviti ovaj uvoz od 63% energije. I kad se pogleda u stvari cjelokupna slika, od kud nam najviše energije dolazi, kakav nam je taj energetski miks, u stvari vidimo da je gotovo sve što uvozimo fosilni izvor energije. Znači skoro 100% svega. I ako pogledamo što u stvari, kako to izgleda, jako lijepo izgleda ovo 71% proizvodimo sami, međutim kad kažemo koliko potrošimo sami, u stvari oko 27% je u stvari nekakva čista energija, a fosilna energija je 72%. Ovo ću u stvari primijeniti nešto kasnije. Ono što je bitno stvarno da imamo, da razumijemo zašto Europska unija, Europska komisija inzistira da se preko svojih raznih dokumenata kao što je zeleni plan, kao što je Recovery EU, gdje se inzistira da se maksimalno proizvodi energija u Europi, odnosno da budemo što više energetski manje ovisni, odnosno što manje ovisni o uvozu. Vraćam se sad na onu elektrifikaciju sustava. Znači, ne govorimo, kad govorimo o elektrifikaciji grijanja, ne govorimo o električnim bojlerima, pa sad bitno je samo da ide to sve na struju, nekakvim, ipak govorimo o sustavima koji su energetski efikasni, koji su i održivi, u stvari koji koriste obnovljiv izvor energije. Naravno, ovdje je primjer jedne toplotne pumpe, u ovom slučaju zrak, ali može biti bilo koja pumpa, gdje imamo jedan impuls 1 kW struje, 3 kW otprilike, 3 kW energije dobivamo iz ambijenta, iz zraka okolinskog, i onda dobivamo tih nekakvih 4 kW energije, i to je nekakva ovako bilanca. Nemojte me sad uzimati kolika je ta energetska efikasnost, to sam uzeo čisto za nekakvo računanje. I sad kad imamo tu, ako smo, poanta je da zamijenimo grijanje na fosilna goriva, na primjer plin, meni je uvijek target nekako plin, ili je on najbolji predstavnik fosilnih goriva, nekako najčišći. I poanta je da ako zamijenimo u zgradi, mi smo u stvari dekarbonizirali onoliko koliko smo mogli, ali priča nije završena. Zašto priča nije završena? Jer postoji ovaj 1 kW električne energije. A taj kilovat električne energije u stvari ovisi kako proizvodimo tu električnu energiju, otkuda, gdje se proizvodi, i naravno još uvijek u Europi, a pogotovo u ovim našim krajevima, našoj regiji, na Balkanu, jako puno toga se proizvodi iz fosilnih izvora energije. Zašto je sad to, zašto je bitno, zašto nam to smeta? Pa to nam smeta radi ovog 1 kW, budući da uspoređujemo emisije CO2 koje emitira jedan plinski kotao, na primjer, u odnosu na toplotnu pumpu. I ako uzmemo nekakav primjer tog plinskog kotla, govorimo o atmosferskim, malo starijim plinskim bojlerima, odnosno kotlovima, koji se i onako mijenjaju, najnoviji kotao koji ste kupili pred 2-3 godine, ne znam, kondenzaciju nećete baš sad mijenjati, ali ako uzmemo otprilike njegova emisija po kilovat satu je oko 235. Toplotna pumpa sama za sebe nema direktnih emisija, sad ne govorimo o ugrađenim emisijama, odnosno onaj embodied carbon, nego govorimo nema direktnih emisija, ali postoji onaj kilovat. Sad taj kilovat, ako uzmemo da je energetska efikasnost nekakve toplotne pumpe između 3 i 4, znači takvom računicom četvrtina, odnosno između četvrtina i trećina tog kilovata, odnosno te energije, se u stvari gleda koliko je vezano za ukupnu CO2 emisiju koja se tiče dizalice topline, odnosno toplotne pumpe. I ako uzmemo jedan primjer iz Srbije, ja sam našao 2 podatka kakav je taj otisak, odnosno carbon footprint struje u Srbiji, i nažalost nisam našao tako optimističan podatak kao što je gospodin Pearson našao jučer ispod 500. Ja se referiram na 2 nekakva izvora koje su znači, nešto viša. U ovom prvom primjeru je 615 taj faktor emisije, i ako to primijenimo računicom na toplotnu pumpu, u stvari dobivamo jedno 150 do 200 grama CO2 ekvivalenta po kilovat satu, i ako usporedimo to koliko je sa plinom, nekakva ušteda je 15 do 35%, što nije sjajno, ali ajde, nešto smo napravili. Ako uzmemo ovaj viši primjera. To je primjer iz prošle godine iz jedne studije koja je rađena vezano za električne automobile, gdje su upotrijebili ovaj faktor znači CO2 emisija za kilovat-sat struje. Dođemo do podatka u stvari da je nekakva emisija, ako uzmemo opet onaj kilovat, sjetite se kilovata, to je 1/4, 1/3 energije koja nam je potrebna za grijanje, dolazimo do podatka 210 do 270, to znači između 200 i 280, i ako usporedimo sa CO2 emisijom plina, u stvari nemamo nikakve uštede. I to je samo nekakav primjer koliko je to bitno da u stvari ta struja koju dobivamo da se i ona dekarbonizira i da se na njoj radi da jednostavno koristimo obnovljive, odnosno čiste izvore energije. Jedan primjer iz Hrvatske, ovo nema veze nikakve sa patriotizmom, mi smo malo imali sreće u podjeli kad se Jugoslavija raspala, pa onda smo dobili pola nuklearke, pa smo dobili isto tako neke hidrocentrale i kod nas je taj nekakav emisije koje dolaze iz struje su manje. Međutim, ako pogledate to, onda automatski, ovdje nažalost nismo jučer uspjeli promijeniti te brojke, ali dobivamo brojke između 50 i 70 grama CO2, znači krivo je napisano, između 50 i 70 grama CO2 po kilovat-satu, što u stvari iznosi otprilike 70 do 80% ušteda CO2. Hrvatska nije najbolji primjer. Daleko od toga. Evo, u Europskoj uniji imate puno nižih podataka, znači puno nižih emisija po kilovat-satu, tako da onda ta ušteda, odnosno smanjenje emisija CO2 je puno veće. I ako uzmemo to na nekakvom primjeru cijele Europske unije, do 2050. godine dolazimo do podatka da se može do 2050. uštediti oko 600 milijuna tona CO2 emisija, što je taj nekakav cilj. I naravno uz uštedu korištene energije, to je onaj dio koji je vezan nekako za direktivu, gdje je direktiva, kako je direktiva gleda i na šta cilja, što se tiče recimo grijanja i tehničkih sustava. Vraćam se opet na nekakav prikaz, jako smo dobili smo predivnu zgradu, kuću, kako god, ona je modernizirana, dekarbonizirali smo i ovu struju, znači ova struja koja dolazi u kuću iz obnovljivih izvora energije, stavili smo i fotonapone na kuću za svaki slučaj, odnosno osamostalili smo se, znači nismo ovisni o vanjskom izvoru energije koliko god je to moguće, napravili smo sve mjere uređenja kuće, promijenili smo prozore, stavili smo fasadu, uredili smo krov, sve smo napravili šta treba napraviti. Napravila država, napravili smo mi, govorimo o nekakvoj 2045. ne govorimo o sutra. I rezultat u stvari cijele te priče je ta mala potrošnja energije, jer smo sve napravili da imamo malu potrošnju energije, efikasni sustavi, izolacije. Ta energija koju trošimo je obnovljiva i možemo ju sami proizvesti. I to je u stvari grubo pojednostavljena direktiva, nekako cilj direktive vizualno gdje se cilja. I ja mislim kad ovako to pogledamo da u stvari to uopće ne izgleda loše. Da čak izgleda jako dobro, a zato zbog toga što izgleda predobro iz današnje perspektive, onda se često puta govori preambiciozno i gotovo nemoguće. Ja se apsolutno s time ne slažem. Čak i sa nekakvog inženjerskog stajališta, ja mislim da su stvari vrlo, vrlo moguće i da ih možemo dostići, ali moramo na tome svi raditi. Dodajem auto, namjerno dodajem električni auto. Ovdje se ne radi o elektrifikaciji transporta, iako bi trebalo i to govoriti. Međutim, taj auto može nam poslužiti u stvari kao baterija. Već danas neki automobili imaju mogućnost dvosmjerne komunikacije, znači da može poslužiti kao nekakav spremnik. U nekakvoj zgradama, kućama gdje to možemo isto tako i o tome razmišljati kao nekakvo rješenje. Znači, to je nekakva cijela priča koja je vezana za vizualno kako izgleda EPB direktiva. Opet ću malo skrenuti, mislim da mi je gospodin Pearson već drugi puta otvorio strašno dobro i hvala lijepa o strašno dobru temu. Ja malo drukčije pristupam. Znači, on je govorio o kako je u nekakvom komercijalnom sektoru, kakva je percepcija energetske efikasnosti, koliko se ta energetska efikasnost u osnovu onoga što imamo na raspolaganju, kako se koristi. Ovo je nekako istraživanje koje je došlo iz rezidencijalnog sektora, evo i vidite po kontinentima. I ako vidite, ovaj nekakav sivi dio je mogući range proizvoda koji možete kupiti energetske učinkovitosti, odnosno efikasnosti, a ova crna crta je šta se u stvari kupuje, šta ljudi u prosjeku kupuju. I ako pogledamo nekako Indiju i Kinu, namjerno sam stavio Indiju i Kinu, jer često podcjenjujemo države, pa kažemo vidi kako kod njih oni kupuju najjeftinije, najlošije, ali ajmo onda staviti Australiju i Ameriku. Onda vidite da u stvari situacija nije ništa bolja. Čak je kineski zakoni su stroži nego američki zakoni. Znači u Americi se može kupiti i lošiji uređaj, ali opet smo u nekakvom ovom najnižem segmentu, ajmo reći, tek dozvoljene energetske efikasnosti koja se može kupiti. Japan i Europa. Strašno razvijeno, super, divno, krasno. Malo morgen. Situacija je u stvari još čak i gora. Evo, pogledajte Europsku uniju, najstroža pravila, a gledajte gdje se nalazi prosječno kupovanje dizalica, odnosno toplinskih pumpi, zrak je ovdje konkretno. Jo? Kupujemo najniže moguće. Zašto? Gospodin Pearson je dao odgovore, odgovori su gotovo isti, neću sve ponavljati, ali ja sam u stvari pitao i ChatGPT da mi kaže koji su razlozi. ChatGPT se složio. U stvari razlozi su ljudi ne mare, nije im bitno, ljudi ne vide benefite, ne zanima ih. Jedna stvar na koju ja nisam mislio, to je u stvari dostupnost na tržištu. Nije na svim tržištima dostupna taj cijeli. Znači, netko kao proizvođač, kao distributer procjenjuje šta će najbolje prodati na nekakvom tržištu i u stvari one bolje uređaje niti ne nudi na tržištu, iako su mogući i dozvoljeni. Znači, svi imamo na određen način obavezu kao struka promovirati i objašnjavati zašto su te stvari jako bitne. Ja ću protrčati malo samo kroz te neke stvari koje su vezane za IPB direktivu, jer će o njoj biti govora i danas kasnije i sutra. A ono što je bitno možda za našu industriju da predviđa se prestanak korištenja plinskih bojlera do 2040. godine. Evo, još imamo 15 dana, pa nakon 15 dana neće se više smjeti financirati, države neće smjeti i financirati i podržavati ugradnju plinskih bojlera. Zgrade će dobiti nekakav pasoš u kojem će pisati sve o tim zgradama, a ono što je jako bitno što se nas tiče i plan unapređenja energetske efikasnosti tehničkih sustava. Zgrade će biti obnavljane prema minimalnim standardima energetske efikasnosti, a to dobro svaka država članica mora sama propisati, što je jako veliki problem. I dobili smo novi naziv standarda zgrada, sad je ZEB zgrada, više nije NZEB ili NZEB. Znači, to su zgrade bez emisije fosilnih emisija i one moraju minimalno 10% biti efikasnije nego NZEB zgrade. Iako opet sa inženjerskog stajališta je vrlo teško prihvatiti te neke definicije, jer imamo definiciju ono koliko je maksimalno moguće. Koliko je maksimalno moguće? Ja to ne mogu. Meni je to jako teško i tko će procijeniti koliko je to maksimalno moguće, ali recimo ovako, ovdje kaže koliko je maksimalno moguće. Države članice to moraju sve napraviti do 2026. godine. Što se tiče novih zgrada, imamo nekakva 2 datuma od 2028. pa do moraju sve javne zgrade biti i ZEB zgrade od 2030. Sve nove zgrade moraju biti po tom standardu, a do tada je sve, naravno, kao što je i danas, taj NZEB standard. I ovisno o površinama uvodi se institut potencijala globalnog zatopljenja, odnosno GWP, gdje se računa taj faktor i na osnovu toga ja pretpostavljam da će u budućnosti biti određena porezna politika koja će biti primjenjiva, znači onaj koji ima preveliki GWP će biti malo bolje oporezovan, malo će više plaćati. A što se tiče postojećih zgrada, najbitnije je u stvari da se treba, da je velika pažnja na zgradama koje su najlošije energetske efikasnosti. I to je ono što je u stvari jako dobro i dobro je da unutar te grupe najlošije energetske efikasnosti se pokrivaju ranjiva kućanstva, odnosno dijelovi stanovništva koji nemaju sami da isfinanciraju tu obnovu, na to se stavlja velika pažnja i mislim da je to jako ljudski i jako dobro, nije uvijek često u zakonima. Što se tiče tehničkih sustava u zgradama, ono što se u stvari želi postići da i koristimo maksimalnu energetsku efikasnost. Maksimalnu, a ne minimalnu koja nam je dozvoljena, kao što smo vidjeli na slajdu nešto prije. I to je ono čemu teži ova direktiva i zato ima onaj pasoš koji kaže gdje se moramo razvijati i kako moramo investirati. Druga stvar koja je jako bitna u ovome je da se konačno unutarnji okoliš, znači unutarnji prostor i kvaliteta u unutarnjim prostorima će se konačno definirati. Opet to moraju napraviti svaka država za sebe, ali prvi puta u stvari se regulira kvaliteta unutrašnjeg prostora, što je znači zrak, osvjetljenje, ugodnost, toplina, koje je isto tako jučer spomenuto u predavanju iz Danske, gdje smo vidjeli da u stvari provodimo, ne znam, 80 ili 90% vremena u zatvorenim prostorima. I ono što je isto nama interesantno kao industriji, da države članice moraju propisati, odnosno podržavati promjenu iz fosilnih izvora energije, odnosno iz fosilnog grijanja u obnovljive izvore energije, moraju sufinancirati takav prelaz dodatno, više nego do sada, a taj cijeli prelaz moraju isto tako naznačiti u svim planovima da se točno zna u kojim koracima će i kada takve mjere na lokalnom nivou biti donesene. Ovaj dio je isto tako samo prepisan iz prošle direktive, znači iz prošle verzije. Ono što je interesantno, u stvari od svega toga vidimo da će se tu pojaviti možda i nekakav nova struka, odnosno pojačati nekakva struka, jer treba će certificiranih stručnjaka koji će pratiti zgrade, koji će kontrolirati, certificirati i napisati koja zgrada kako treba se uređivati i na koji način treba napraviti taj nekakav update da bi došlo do nekakve zadovoljavajućeg stanja. Bitna stvar je u stvari isto koja nije još definirana skroz, ali je integrativnost svih sustava. Znači svi sustavi predviđa se da će u nekakvom cloudu funkcionirati zajedno, da će komunicirati međusobno. GDPR se još nije definirao, ali bit će i to, na tome se radi. Ono što je u toj cijeloj priči bitno da ćemo koristiti, i to je spomenuto sad malo prije u predavanju, koristit ćemo točno onoliko energije koliko nam treba. Vi danas imate, kad zakupite 9 kW, vi u svakom trenutku imate 9 kW na raspolaganju, što je nerezonski, stvarno, jer ne trebate. Vi trebate to ponekad. I onda ćete imati, jednostavno, kad nećete trebati, nećete ni imati. A cijene će biti, a već je to sada u zapadnim državama, je već to sada dinamičke cijene, morat će, kao što je gospodin malo prije izjavio, treba ćemo se priviknuti na to da je struja jeftinija po noći, da će biti skuplja po danu, odnosno da između 5 i 6 je struja možda najskuplja ili će biti jeftinija. Znači na taj način ćemo funkcionirati, a to je pitanje isto i takve integracije. Dekarbonizacija, u redu, energetska efikasnost toplotnih pumpi. Još ono što je jako bitna priča, dekarbonizacija naravno električne energije, struje, međutim bez ovog zadnjeg segmenta nećemo napraviti gotovo ništa. Ovdje je prikazano koliki je omjer cijene između kilovat-sata struje i kilovat-sata plina. U Hrvatskoj je to prošle godine bilo 3,6. Jednostavnim računom, ako imate energetsku efikasnost ispod 3,6, ne možete uštediti ništa. Financijski. Štedite vi na energiji, ali financijski ne možete uštediti. I ako se na to neće paziti, a u našim državama se tu, uključivo i Srbiju, i Hrvatsku, i Bosnu i Hercegovinu, Crnu Goru, a i okolne države isto Evropske unije, dosta se subvencionira i pogotovo se subvencionira plin. Jednostavno, ako ta razlika prelazi nekakvih 2, mi nemamo ljudi nemaju interesa financijskog da rade dekarbonizaciju, znači to bi sve išlo na silu. U Srbiji je situacija nešto bolja, nešto ispod 3, to je zadnji podatak koji sam izvukao iz Blica kad sam preračunavao struje, kolike su cijene struje i kolika je cijena plina, međutim i 3 je preveliko. Ako gledamo neke države koje su jako napredne po tom pitanju, recimo jedna Bugarska ima 1,5, naravno da onda je vrijeme povrata investicije u toplotnu pumpu je jako kratko. I ako uzmemo sve te stvari u obzir, u stvari ta direktiva i takav nekakvi smjer je vrlo prihvatljiv ako znamo da nam čini benefit, da nam čini dobro na nekakav duži rok, ja mislim da nemamo alternativu. Hvala vam lijepo.
Hvala Hrvoje, prezentacija je bila interesantna, mogli bi sada da pričamo mnogo o primarnoj energiji, ono što je potaknuto ovim izlaganjem, posebno mi znamo da se kod nas najveći deo toplotnih pumpi pogoni pomoću električne energije koja se proizvodi u termoelektranama koje koriste ugalj kao sirovinu.
U Srbiji je ovako podatak da je 3/4 svih emisija CO2, znači svih emisija CO2 dolazi iz proizvodnje električne energije.
60% električne energije se proizvodi iz uglja kod nas. Sad, ja bih hteo da obavestim skup da mi imamo danas popodne negde oko 4 sata u ovoj susednoj sali, u sali 2, imamo jedno lepo predavanje sprege split toplotnih pumpi sa fotovoltaik praktično panelima koji proizvode električnu energiju. To je neka stvar budućnosti. Sada su u poslednjih par meseci Amerikanci su izbacili split sisteme koji imaju rashladnu snagu od 3,5 do 7 kW, ali koji su direktno povezani sa fotovoltaik panelom koji ne zahteva inverter, koji ne zahteva bateriju, nego se direktno vezuje na kompresor. To su sad neke nove stvari koje će dati mogućnost da se smanji emisija CO2. Jer mi sada pričamo o COP, nama je COP kao glavni faktor za određivanje kvaliteta toplotne pumpe. Mislim da to nije, da postoji PER, a PER je primarni energetski odnos koji treba da kaže koliko primarne energije mi trošimo da bi dobili ono što hoćemo u smislu grejanja ili hlađenja.
Koliko je primarni energetski faktor sada u Srbiji?
Ne, to ne znamo, ali znamo da vazdušne toplotne pumpe koje koriste vazduh kao izvor toplote imaju PER nešto iznad 1, a gasni kondenzacioni koto je tu negde blizu 1. Tako da tu su praktično pitanja da li gasni koto je toliko loš, normalno modern gasni koto koji ima visok stepen efikasnosti u odnosu na toplotnu pumpu. Hvala vam. Ja plašim se da nam beži vreme i moramo da pređemo na sledeću temu. Hvala gospodine Krapaniću. Interesantno je bilo predavanje. Sledeće predavanje će da nam izloži Dušan Čajić. Tema je primjena amonijačnih lipnih kompresora kod visokotemperaturne toplotne pumpe u kaskadnom rashladnom sistemu CO2 amonijak snage grejanja do 2 MW, primjer iz prakse. Izvolite, gospodin Dušane.
My presentation will be on English language, so I don't think you will need a translator for this. Thank you all for coming. Since it's already past 12, I wish you a good afternoon. And thank you for participating at this presentation. As the board already mentioned, we will talk about high temperature heat pump installation integrated into the cascade standard CO2 ammonia cascade system. On this slide, as you all know, due to the worldwide geopolitical situation and many other factors that influenced the high increase of the energy price, especially in the European Union, many industries started looking for alternative applications that could reduce the amount of energy used, consumed, and the price at the end. We all know that industrial refrigeration systems are some of the major energy consumers, and it was a logical thing to put the focus on finding alternative solutions, especially at these systems. For this particular project, we have decided to go with the CO2 ammonia cascade refrigeration system due to some comparative advantages comparing to standard ammonia systems or even transcritical CO2. I will not go more into details. There are some advantages that we can discuss, but I believe that for every particular project there are some advantages for one or the other selection. We know that energy efficiency for low temperature and low pressure systems goes toward the cascade system because of the very good thermodynamic characteristics of the CO2 on the low stages. On the other hand, we have a safety reason because with this system we send CO2 to the cold rooms and we don't have risk of pollution if some major leakage occurs. And due to that, we reduce the amount of ammonia in a total system, which means we will have ammonia framed only in the machine room, and this is particularly beneficial for the companies when they are obtaining the licenses and the working permits because local codes and standards allow them some easier procedures to get those permits. Compared to transcritical CO2 systems, again, we can find some energy efficiency, especially when the outside ambient temperature goes high because transcritical CO2 systems lose their efficiency, particularly when we have high ambient temperature. And also with this cascade system, we have lower operating temperatures and pressures, which at some point can be beneficial due to lower investment costs for some parts and the materials that request lower pressure. I will just go shortly through the basic description of the CO2 ammonia cascade refrigeration system. As we already said, we have on the pH diagram two circuits. The lower one is the CO2 circuit, and the top one is ammonia circuit. As you can see, those two blue areas, the lower left one represent the increase in the total refrigeration capacity of the system. And on the right corner, we have a blue area that represents reduction of the work on the compressors. This part here, this slide, represents a simplified PNID for this particular refrigeration system that we installed in the distribution center in Austria. This was done in cooperation with Johnson Controls. And as you can see on the left side, this is just the standard refrigeration CO2 ammonia system that has minus 36 evaporation temperature, around 750 kilowatts of cooling power. And we have a dry suction going to 3 piston compressors. They have a unique hot gas discharge going to CO2 condensers, which are, on our opinion, first crucial point of the system because these two CO2 condensers are also working as ammonia evaporators, and these items, these units has to be very well manufactured with high-end materials because on our opinion, if the leakage or the damage occurs on these heat exchangers, it can create a major breakdown of the system. And the rest of the system from the ammonia side is pretty much standard refrigeration system. We have a dry suction going to piston compressors for the ammonia, and we have a hot gas discharge going to nowadays standard design, which goes through the heat exchanger for a recovery system. And after that, we have a motor valve that goes to the next crucial point of this system. our investor requested from us to install this high temperature heat pump and integrate it into the existing system, a refrigerating system. Usually we do this by completely independent system, but for this application, we were not able to use evaporative condensers. Rather, we installed horizontal type of air coolers that can work both way. First as standard condensers when we have a standard and normal refrigeration mode. And if we want to switch to a heat pump mode, they work as ammonia evaporators, and they collect ambient heat from the outside and push it over the heat pump system. On the right side, the side that is in the cloud, this is basically our heat pump system with the high temperature ammonia heat pump. And we have 2 piston compressors, which have on the discharge side high temperature hot gas that goes over 133 degrees, and with the condensing temperature of 84 degrees, we go to the heat exchangers. On the other side of the heat exchangers, we have 2 circuits, the primary water circuit, which is only for safety reasons, and the second one, which is actually the major secondary water circuit that delivers the 80 degrees water to the buffer tank for the heating system. And right above the buffer tank, we installed the measuring unit with the flow meters and temperature transmitters, and that way we were able to monitor the complete system and the real heat energy that we deliver to the heating system. On this slide, you can also see some more details about the PNID, but since we are framed with the time, I will just briefly go through it. I would just mention this ammonia condenser, which is now horizontal type, and as you can see, there is a very complex system of valves and valve stations with different sensors that allow us fully automatic running of the system and the transferring from standard refrigeration system to the heat pump mode. Here, these are just some comparative advantages of the piston compressors toward the standard screw compressors. I will not go more in details. You will have everything on the slides. Basically, what we realized is that the work efficiency is better with the piston compressors and partial control of the capacity, because we know that screw compressors are mostly effective from over 40% of load, and for piston compressors we can go between 10 and 15% of load up to the maximum load. Also, piston compressors behave better on higher pressures and temperatures. We know that we have problem with the oil cooling on the higher temperatures with screw compressors. From the reliability and the maintenance point, what is the benefit with piston compressor is that we can target maintenance. We don't need to do overall maintenance, and service hours are a bit longer. And economy-wise, well, this is one of the points where we always have to discuss with our partners and investors at the end, because screw compressors, of course, they have lower initial costs, and later during the maintenance and working mode, they have increased operating costs, and vice versa. The piston compressors, they have higher initial costs, but later they become more effective during the maintenance. For this particular project, we were designing with the HPX 712 VSD. This is Sabra compressor, which is designed particularly for heat pump, ammonia high temperature heat pumps, and it's designed based on previous CMO and SMC compressors. Here you can see some details. It has a theoretical volume from 100 to 1100 cubic meter per hour. It also works in a different range of motors installed. It can work from 75 to 250 kilowatt. On some special applications, the motor can be even bigger, but then we have to put special care on the design of oil cooling. And what is particularly interesting for this compressor, when it works in a heat pump mode, is that on the high side, it works with operating pressures up to 60 bar. Like every other or most other Johnson Controls and Sabro compressors, it has Unisub controller, which is integrated into this package. Here we have just several details. On the left side is the data sheet from the matchmaker, which gives us more details about this particular application. We can see the evaporating and condensing temperatures and pressures. We can see selected motor and some more details about the oil cooling. On the right side here, we have operating range for this compressor, and for our application, we see that it's in the area 1, which means we will use just the standard oil cooling. And on the bottom, we have a simplified flow chart for this compressor, which shows us that actually on the discharge side, we have over 130 degrees Celsius of the temperature and over 45 bars of operating pressure. I will try to make my presentation as short as possible because we are already a little bit delayed with time. As I mentioned before, we were able to put some measuring units, so we are able to measure electricity consumption and power delivered to the system. First diagram represents the electricity consumption for the entire refrigeration system, and the second one represents the consumption of the 2 piston compressors for the heat pump. Theoretical calculated COP for this system, well, it is a semi-theoretical because we were already testing this system before, but we were taking that information from the data sheet, and the COP for the heating side should be 4.5. And when we take the information from the measuring unit, and we have 2.08 megawatts of electricity consumption from the heat pump compressors, we can calculate that theoretical calculated heat energy that is delivered to the heating system should be around 9 megawatt hour. And this is all measured in the 24-hour period for the testing. The system is new. It was installed by the end of last year, and we are expecting more details and measuring during this winter because we expect that we will have a full load of heat pump during the several months in that area. The next slide represents also 2 diagrams. The first one is just the time schedule for the compressors that goes on and off, and it was set up by the system to have switching between 2 compressors to follow their working hours. And the last diagram for us was the most important, and this is the measuring of the heat energy that was actually delivered to the buffer tank and the heating system. From this diagram here, we can see that actual measured heat energy that was delivered to the buffer tank was 9.5 megawatt hour in the period of 24 hours. And since we in the previous diagram saw the actual electrical consumption that was already measured, we were able to calculate this realistic COP that was given and produced. As a conclusion to this, we realized that this system is proven to be best and mostly used for the distribution centers and productions where we have simultaneous demands for cooling loads and heating loads at the same time. And also, since we are using piston compressors, we realized that it's very convenient for the systems where we have very large daily oscillations of the load, so we are somewhat able to preserve the energy that we need for the heating. On the other hand, of course, with using the CO2 and cascade system, we are reducing the negative impact that we have on the environment specifically, because as I mentioned before, we reduce the amount of ammonia that is now framed to the machine room, and everything else in the system goes with the CO2 through the cold rooms. I don't want to waste a lot of time because all these details you will have in the presentation, but if you have any further questions, let me know. If not, thank you all for listening to me.
Hvala kolegi Čajiću na ovako lepoj prezentaciji. Ima li neko pitanje? Any question? Mi nemamo baš mnogo vremena, zahvaljujem se još jednom kolegi Čajiću i svi dobijaju ovako neku diplomu. Ja bih zamolio da ostanete tu. Mi sledeća prezentacija je planirana da održi gospodin Dejan Đurović, ali on je, vidim da nije tu. Evo ga, odlično. Taman sam ja hteo da držim prezentaciju umesto njega. To je, koliko ja znam, prvo takvo postrojenje. Hvala. Mislio sam da mi pomognete oko priče, oko ove instalacije, pošto je prva takva instalacija gde je amonijačna toplotna pumpa spregnuta sa čilerom koji služi za proizvodnju. Prva takva, koliko ja znam, u Srbiji. Prošle godine je to bilo u fazi projektovanja i gospodin Đurović je prezentirao taj početak, start na ovom projektu. Rad, odnosno naslov rada koji će nam izložiti instalacija i testiranje parametara rada visokotemperaturne amonijačne toplotne pumpe u industriji proizvodnje bezalkoholnih pića Coca-Cola Hellenic Bottling Company Beograd. Izvolite, gospodine.
Hvala puno. Gospodo predsedavajući, poštovane koleginice i kolege, kao što je kolega najavio, zapravo ova prezentacija i ovaj rad je nastavak one priče od prošle godine, kada je sve to bilo samo u nekoj priči, u nekom početku zapravo projektovanja, a sada je to, da kažem, završeno i u toku je testna faza testiranja. Malo samo da se vratimo na početak cele priče, da malo osvežimo šta je to i kako je to bilo i kako je išlo, koja je tu u stvari bila i motivacija celog ovog projekta. Zapravo da se smanji, dakle, emisija CO2 koju mi imamo kao target, kao jedna od 29 zemalja, članica Hellenic Bottling Company, Coca-Cola grupacije za Evropu. Mi imamo stalno targete, ciljeve koji su sve stroži i stroži iz godine u godinu i odnose se čak i na nas koji nismo još uvek deo Evropske unije i koji ne moramo da se prilagođavamo nekim onim strožim zakonima, međutim, nas, da kažem, grupacija tera na to. Tako da mi stalno moramo da dajemo projekte, da dajemo predlog ideje da se smanji potrošnje, da se smanji emisija CO2, da se smanji potrošnje energije i naročito, osim struje, naravno tu i prirodnog gasa. Sa druge strane, svedoci smo, to je i definitivno i potvrđeno, jel? I zvanični podaci tako govore da je ovo leto bilo najtoplije ikada od kad se meri temperatura. Tako da prethodni rekao, i to je važilo za celu severnu hemisferu, i za celu Evropu, pa tako i nas, svedoci smo bili kako su to bile vrućine ove godine, da je to praktično svake godine sve to duže traje i sve su više temperature, tako da definitivno moramo svi zajedno da poradimo na tome da se smanji emisija gasova sa efektom staklene bašte, da se koriste obnovljivi izvori energije u što većem obimu i naravno da se primenjuju što više projekata energetske efikasnosti, jer samo to je način da možemo da na neki način makar malo usporimo sve ovo što nam se dešava i čega smo svedoci, ali definitivno to je neka naša nova normalnost. Kao što je kolega i najavio već, to je prvo takvo postrojenje gde je spregnuta amonijačna toplotna pumpa sa čilerom i definitivno je prvo u celoj grupaciji od 29 zemalja koji čine Hellenic grupaciju. Kako je išao razvoj projekta? Dakle, mi smo prvo želeli da definišemo koje to sve imamo potrošača u okviru fabrike, a inače imamo 9 proizvodnih linija, 6 SSD, znači to su gazirani za proizvodnju gaziranih napitaka i 3 za proizvodnju džusa. Znači da definišemo koji su sve to potrošači, znači fabrika je dosta velika, vodi se kao mega plant među svim fabrikama u grupaciji. Šta smo mi uradili? Mi smo prvo uzeli i izmerili i angažovali smo, dakle, izvođača koji će da nam uradi merenja na svim izmenjivačima toplote, pošto je fabrika u isto vreme dosta stara i stalno se radila neka nadogradnja i dopuna postojećeg sistema, tako da je bila ideja da prvo definišemo potrošače, da definišemo koje su to snage i koji su to temperaturski opsezi. Znači, to je ono što je u stvari bilo ovde i najvažnije. Jer kada, kome god sam pričao ranije, na početku cele ove priče oko toplotne pumpe, svi kažu, a tebi treba toplotna pumpa. Super, imam rešenje za tebe. Ok, koje su temperature? Pa 60-70. Nažalost, to nama ništa ne igra. Nama igraju samo temperature koje su 85-90 i više. Dakle, uradili smo ta merenja, izvršili analizu dobijenih rezultata i onda počeli da radimo pripremu projekta i samo projektovanje. I naravno da razvijemo finalni koncept ovog celog projekta. Na ovom slajdu je prikazana tehnološka šema. Zbog svoje složenosti, kao što možete videti, dosta je kompleksna, što i jeste zapravo i u stvarnom, da kažem, u stvarnom životu jeste tako, jer ovo što je prikazano ovde crvenom linijom, to je granica projekta nove opreme koja je instalirana, a sve ono što je van toga, to je oprema, to su mašine koje su već postojale i koje su spregnute sa ovom toplotnom pumpom. Tako da sa jedne strane, na izvoru, imamo chiller snage rashladne 1 megavat, koji je spregnut sa toplotnom pumpom. Dakle, chiller se koristi za potrebe u procesnom hlađenju. Radi u režimu 6-10 i on je spregnut, on je u prvobitnoj zamisli, znači on ima svoje 2 rashladne kule, pošto je vodom hlađen chiller, ima 2 rashladne kule, gde se, dakle, ta voda iz kondenzatora hladi u rashladnim kulama, dakle, baca se energija. Sada je tu umetnuto između, mislim da je ovo pointer, ili nije, kako god, vidi se, dakle, umetnut je između chillera i rashladnih kula, umetnut jedan buffer tank od 35 kubika zapremine vode, koji predstavlja, gde se, da kažem, lageruje voda, znacima navoda, kao izvor za toplotnu pumpu. Temperatura te vode u tom buffer tanku se kreće u rasponu od nekih 35 do 40 stepeni i predstavlja izvor za toplotnu pumpu. Dalje, toplotna pumpa sa druge strane, na toploj strani, da kažem, zagreva vodu u drugom buffer tanku, da opet zaprime 35 metara kubnih, na temperaturi od 85 do 87 stepeni. Gde se, dakle, nakon toga ta voda kasnije iz tog buffer tanka distribuira dalje do izmenjivača toplote, koji služe za zagrevanje mešavine vode i kaustične sode u mašini za pranje staklene ambalaže. To izgleda ovako. Znači, ovo je mašina za pranje staklene ambalaže, ima 2 kupatila i samim tim ima 2 izmenjivača toplote. Pre ovog projekta se koristila suvozasićena para, koja je zagrevala tu mešavinu vode i kaustične sode na temperaturi 80 do 84 stepena i na taj način se tretirale su se flašice koje prolaze kroz tu mašinu za pranje. Ovo je ono o čemu sam pričao, dakle, ovde se može videti na ovoj slici chiller, ROS sa rashladnim kulama. Na kondenzatorskoj strani je snaga 1,2 megavata, dok je na strani, da kažem, isparivača na toplotnoj pumpi snaga 620 kilovata. Što znači da otprilike, kad chiller radi sa pola svog kapaciteta, može apsolutno, dakle, da jednu ovu kulu zamenimo, da se zameni toplotna pumpa, praktično menja jednu potrebu jedne kule. Evo ovde možete vidjeti taj spoljni sud, znači buffer tank, 35 kubika, u kome se, da kažem, spremište vode od 35 do 40 stepeni temperature, koje predstavlja izvor za toplotnu pumpu. A ovde možete videti, dakle, jednu prostoriju koju smo morali naknadno da izgradimo, za potrebe smeštaja ovog drugog buffer tanka na toploj strani, gde je temperatura vode u tom tanku između 85 i 87 stepeni. Takođe smo ovde predvideli i mogućnost da u budućnosti širimo kapacitet, tako da smo odmah u startu napravili mnogo veću ovu prostoriju, gde će osim ovog tanka u budućnosti ovde staviti još 3 druga tanka za potrebe CIP-a, a to je ono skraćenica clean in place, znači za čišćenje linije, ono kada se proizvodi, kada se menja ovaj ukus proizvoda koji se radi, tada ide taj takozvani CIP, tako da u smislu projekta proširenja i upgrade-a kapaciteta na toj strani, tu je predviđeno odmah i ugradnja dodatnih tih tankova, koji će opet mogu koristiti ovu toplu vodu za zagrevanje vode i kaustične sode. Ovde možete videti toplotnu pumpu koja je instalirana u postojećoj čilerskoj stanici, GEA toplotna pumpa, 800 kW na toploj strani, takođe sa svim, dakle, onim preporukama koje se rade sa detektorima za curenje amonijaka. Takođe bio je zahtev od GE da se to smesti u zasebnu kućicu, znači nije za spoljnu ugradnju, već za unutrašnju ugradnju i tako i učinjeno. Ovde možete i videti slike prilikom instalacije same pumpe sa svojim pratećim elektroormanom i naravno ovde sam prikazao neke slike sa samog panela za rad toplotne pumpe, gde se može vidjeti u tom trenutku je bila temperatura nekih 80 stepeni na potisu, target je bio 85, tako da za ovo što smo malo vremena koliko smo imali da od momenta završetka instalacije cele opreme, imali smo svega možda 10-ak dana za neko probno testiranje, tako da testiranje još traje, ali ono zasad što smo uspeli da vidimo da pumpa i ceo taj sistem, koliko god on bio onako glomazan i kompleksan i tako dalje, uspeli smo sve da uparimo, uspeli smo sve to da sinhronizujemo, tako da pumpa daje tih očekivanih 85 stepeni bez ikakvih problema, tako da se tankovi relativno i brzo zagreju i vrlo brzo možemo da pustimo tu toplu vodu za potrebe procesa proizvodnje. Ovde možete videti i panele sa, da kažem, koji prikazuju hladnu stranu i koji prikazuju toplu stranu toplotne pumpe. Što se tiče opravdanja samog projekta, ovo je ono što je bilo izračunato, kad smo radili sam projekat, dakle, gde imamo godišnje uštede na prirodnom gasu, imamo trošak, naravno, sada struje za potrebe rada toplotne pumpe i vidimo na osnovu investicije da je to neki povrat blizu 8 godina. Sad dolazimo do one priče čemu sam na početku pričao. Dakle, nas kako ta naša grupa gura da implementiramo i neke vrednosti koje nismo obavezni, na primjer, kao da kod nas već vazi F-gas regulativa, CO2 takse i tako dalje. Tako nam oni omogućavaju da bismo projekte koji su veoma dobri mogli da opravdamo. Oni nama dozvoljavaju da mi koristimo u proračun za ovakve projekte gde se očekuju velike uštede na emisije CO2, da koristimo kao da ćemo dobiti uštedu na osnovu CO2 takse, zato što sama grupa plaća tu taksu. Kada se to sve uzme u obzir, naravno, i preračuna ponovo, dobijemo da je onda povrat investicije 4 godine, što je sasvim prihvatljivo i onda smo mi, naravno, dobili opravdanje za ovaj projekat, dobili sredstva i krenuli u investiciju. CO2 emisije, kao što sam rekao, znači nekih 14%, smanjenje prirodnog gasa 12% i ono, naravno, sada što nam prestoji je svakako dalje testiranje i puštanje u finalni rad celog ovog sistema. Sledeći korak jeste nabavka nam ide novog čilera. Želimo, naravno, i on da bude vodom hlađen sa, naravno, preporukom sada da više ne možemo da kupujemo freonske čilere, sada definitivno moramo da idemo sa amonijačnim. I, naravno, tražimo nove potrošače u okviru fabrike gde to možemo da plasiramo tu energiju. To je, kao što sam rekao, taj CIP za čišćenje linije, grejanje fabrike, onda određeni koraci u pasterizaciji na proizvodnji džusa, pošto tamo dosta su visoke temperature koje idu i preko 100 stepeni u nekim koracima, tako da može za neko predgrevanje te vode u pasterima. Da bismo naravno na kraju došli do nekog finalnog koraka, to je Zero Natural Gas Consumption, to je ono što imamo mi kao na strane naše grupe, da do 2040. Moramo da ostavimo taj net zero consumption, odnosno to je ono mereno slično kao što se u Europskoj uniji radi, znači mereno na neku referentnu godinu, za njih je to 2017, ako se ne varam, tako da u odnosu na tu godinu, znači da nema povećanja potrošnje emisije CO2. To je ukratko sa moje strane. Hvala vam na prilici da prezentujem.
Hvala gospodine Đuroviću. Ja bih samo hteo da napomenem da je kolega Čajić jedan od učesnika u tom projektu i projektant na tom delu. Ja sam imao čast da budem prisutan i da pratim ispitivanje ovog sistema. Ono što mi se čini da je značajno, a kolega Đurović nije rekao, to je da je punjenje ove amonijačne toplotne pumpe ispod 50 kg amonijaka, a da pritisci koje smo tamo videli i merili su preko, pritisci kondenzacije su preko 40 bara. Znači, ja kad sam bio mladi inženjer i kada smo radili amonijačne instalacije, kad bi pritisak prešao preko 13 bara, 13 do 15 bara, mi smo se već hvatali za glavu. Ovo je sada radilo, znači, na pritiscima kondenzacije preko 40 bara. Izvolite, gospodin Stajiću.
Jel se čuje? Čuje se.
Da.
Ja imam pitanje u vezi uštede CO2. Pre svega, koliki je koeficijent grejanja za toplotnu pumpu?
4.
4. Sa našim ovim electricity grid emission factor koji je 500-600 i koji je katastrofa, otprilike 2, odnosno 3 puta veći nego što je neki prosjek Europske unije, ja moram da sumnjam da sa koeficijentom COP 4 vi možete da napravite bilo kakvu uštedu u emisiji ugljen dioksida. Budući da, ako sam dobro razumeo, time ste zamenili gas, je li tako, potrošnju gasa. Znači, kad gledate oslobađanje CO2 u gasnom kotlu i kad gledate toplotnu pumpu sa koeficijentom 4, ja moram da sumnjam da ste vi postigli uopšte uštedu CO2, izvinjam se. Nadam se da je to neko proračuno.
Ne bi da otvaramo diskusiju oko toga, znači,
prvo,
ja sam pratio...
Pitao sam čovjeka, nisam pitao tebe.
Ja sam pratio, ti ne možeš da sumnjaš u nešto što je...
Može čovjek da mi odgovori.
Izvor energije je topla voda temperature od 35 do 40 stepeni. Znači, temperatura izvora je vrlo visoka. Temperatura vode koja se postiže, koja se traži u procesu je do 85-87 stepeni, ali normalno je da oni gledaju da obave proces i sa nižom temperaturom vode.
Kako to ima veze s mojim pitanjem?
Pitanje je to zato što sa tim visokim temperaturama izvora i sa temperaturama ponora koji su ispod 80 stepeni, taj COP je i preko 4. Ne možeš ti sad da kažeš ja sumnjam.
Dobro, ali mogu ja da... Mislim, ja bih volio da mi autor rada odgovori, ne znam u kom svojstvu mi ti odgovaraš, ali, znači, čovjek je rekao da je 4.
U svojstvu predsedavajućeg.
Ja kažem, pa ne pitam tebe, ja kažem da sam radio za sebe neke računice sa našim faktorom emisije, budući da mi dobijamo struju iz uglja i dobijamo toplotu, vi dobijate iz gasa, i da nikako nisam mogao sa koeficijentom 4 da dobijem neku značajnu uštedu u emisiji ugljen dioksida. Ništa drugo. Pretpostavljam da ste vi to dokazali.
Naravno, zato što možda nisam napomenuo, električna energija koju mi kupujemo je sa 100% sertifikatom da je potiče iz obnovljivih izvora energije. Tako da to je jedan ključ i drugo je naravno da koristimo prirodni gas a računica je apsolutno tačna, tako da nema nikakve sumnje da ne znam zašto dovodite to u pitanje, ali
Ne, ali
to je vaša stvar, okej.
Vi ste mi odgovorili na pitanje, znači što je potpuno logično. Ako imate sertifikat da dobijate struju iz obnovljivih izvora, što mi Peja nije odgovorio, da ne znam da li zna, onda to ima logike. Iako sam ja diskutovao dosta sa ljudima o tim sertifikatima, o toj proizvodnji, i ako sam ja dobro razumeo, ali kažem to, nemojte lično da shvatite, interesovalo me. Znači, elektrodistribucija Srbije pojma nema koji deo struje iz obnovljivih, koji nije iz obnovljivih, oni to uopšte nemaju razvojeno, to je sve ista struja koja ide ne znam odakle, i imati takav sertifikat je, ne znam, nije neka prednost.
Ne, prednost jeste, zato što vi dobijete sertifikat da to jeste potiče, mislim, ne znam zašto vi to sad govorite da oni nemaju pojma, sad ispade da oni ne znaju ništa, ne bi se složio sa tim, dakle, oni u svom miksu imaju toliko i toliko gigavat sati proizvedene struje iz uglja, toliko i toliko gigavat sati proizvedene energije iz obnovljivih izvora, plus možda ima nešto iz strane uvoza ili nema, kako god, tako da oni to što imaju tih, karikiram, 100 gigavat sati iz obnovljivih, oni to ponude na tržištu. Ko se javi, kaže ja hoću to da kupim, okej, to ima svoju cenu, neko to kupi, uglavnom to kupuju strane velike kompanije kao što je Coca-Cola i mnoge druge, i prosto to je tako. Sad, znate, ne možete vi sad da kažete, sad ja kad ubodem u ovaj šteker, ja sam sad baš uzeo 2 kilovata iz vetrogeneratora. Pa da, ali to ne može tako da se gleda. Znači, oni u svom miksu imaju 100 ovako i 350 ovako, karikiram. I to je to. Oni ponude na licitaciji ko hoće to da kupi, ko hoće kupi, ko neće ne mora i to je to.
Hvala gospodine Đuroviću, hvala Zorane Stajiću. Mi imamo još jedno predavanje, ja bih da pokušamo da završimo ovu priču. Sledeće predavanje je procesna jedinica za skladištenje toplotne energije u kombinaciji sa toplotnom pumpom vazduh-voda. Predavač je gospodin Yildiz. Ja sad ne znam kako se čita ovaj Kacali Univerzitet Turska. Floor is yours.
Okay, thank you very much for your patience and attendance to my presentation, which is the last one. That's why I would like to make it quite concise, but I won't also skip the important parts, of course. So my presentation is about assessment of a thermal energy storage unit, which is coupled to an air source heat pump to be used in the residential heating processes for building heating and so on. First of all, I would like to start with the main scope of the work. However, before that, I would like just briefly mention about what thermal energy storage is and how and why we do it in residential heating system especially. Thermal energy storage can be done mainly in 3 major ways: storing heat in sensible form, in latent form, and in thermochemical form. Thermochemical energy storage is yet to be researched, and still a lot of research is ongoing, and it's a complex process. However, the other 2 is very popular at the moment: sensible energy storage and latent heat storage. Apart from them, latent heat storage comes one step further, because using latent heat storage, you can store thermal energy in nearly isothermal conditions and with phase change materials, changing their phases from liquid to solid or solid to liquid, you can store and release a significant amount of thermal energy. So, integration of these thermal energy storage units to heat pumps can be also categorized into 2. You can either implement this onto the condenser side or evaporator side. In this work, we try to cope with it by integrating the thermal energy storage unit to condenser of a heat pump, to an air source heat pump. And first, we try to store heat by heat pump, by operating heat pump, and then we use the pre-stored heat without actually operating the heat pump. The aim is actually shifting the loads from off-peak periods, because we always emphasize on electrification of the heating system. However, when we do this, either with, it doesn't matter actually, with fossil fuels or renewable sources, we pushed the electric grid a lot of load. That's why we need to reduce this. In order to reduce this, we need to shift it to the off-peak periods. Therefore, in this work, we are going to quantify the performance of thermal energy storage unit using PCMs and also with water for the comparison. And the study can be divided into also 2 steps. First, experimental step, and then numerical implementation. We established a numerical model, a validated numerical model using the experimental obtained data. So experimental setup consists of a multi-source heat pump rig, experimental rig in the laboratory conditions, and we implemented a thermal energy storage tank to this heat pump, which has 32 identical PCM tubes inside. So the PCM tubes and water have a heat exchange among each other. Thermal energy storage with PCM is integrated, as I said, to the condenser unit of the heat pump. And the condenser of the heat pump is accumulated with a hot, coupled with a hot accumulation tank. So a chiller unit is used to reject the pre-stored heat from the thermal energy storage unit, which simulates the heating load, such as a building. And the on-peak periods, of course, I have to add that the electricity prices are also charged very high in the on-peak periods in order to encourage people to use electricity during the off-peak periods. So going with the methodology of the experimental setup, we measured the water and PCM temperatures from different locations in order to monitor the variations regarding different locations, of course, and regarding time. And the electrical energy consumption of the compressor was also monitored with a network analyzer. And all data was converted and logged in a computer, of course. And the procedure is like that. So the thermal energy storage unit constitutes the heat sink of the heat pump, and therefore thermal charging process, which means that we heat up the water inside the thermal energy storage tank using the air source heat pump from 35 degrees Celsius initially to 55 degrees Celsius. And then once this temperature is reached, 55 degrees Celsius, the thermal charging operation is ceased, it is terminated, and then thermal discharging is immediately started from 55 degrees Celsius to 35 degrees Celsius. And by doing this in the experimental conditions, we have taken into account different heating loads ranging from 3 to 12 kilowatts. As a PCM, as a phase change material, we used lauric acid, which is a fatty acid-based PCM, because it's favorable thermophysical properties, which are shown in the table. It is suitable for the temperature range we operated, because the phase change temperature should be between the upper and lower limits of our operation of heat pump. Actually, the thermal charging and discharging temperature limits. Besides, it is also a well-known material for thermal energy storage, and it is cheap and easy to find, actually. Going with the numerical model were conducted for 4 different PCMs, because once we establish the model, it is easy to implement other PCMs and so on in the model. But we held the heat rejection rate at 3 kilowatts to make the comparison simpler. But it can be also another parameter also. The water inside the thermal energy storage tank was considered a lump system in regard to the experimentally obtained data, because in the experimentation we observed that the temperature did not show significant change with respect to locations, because we measured the temperature in axial and in radial directions. Therefore, we didn't see actually so much differences. Besides, the heat transfer through the PCM in the tubes was handled by one-dimensional conduction, yet the natural convection effects could occur when the PCM once liquefies, because the liquid can move up and down circulating due to density variations. However, we treated this by a Nusselt number correlation, which is established for phase change materials in vertical tubes, which is adequate and appropriate for us. The thermophysical properties in the table are given for different PCMs, which are used in the numerical model. And these include, for example, RT38, lauric acid, as originally, and RT44 and RT47. The numbers after these terms represent the phase change point of these materials. And these are commercial phase change materials from the company Rubitherm in Germany, which is widely used. But of course, their latent heat capacities are as an important parameter, is an important property, and that's why we can also pay attention that they are different. So the numerical model in detail can be shown as follows, and the blue frame shows the thermal charging by heat pump. In this case, the pumps on the right-hand side are inactive, and the air source heat pump only charges the thermal energy storage tank. And in this case, we model the internal energy change of the water inside the thermal energy storage tank by the following differential equations. And in this case, the load is 0 during charging, and the condenser load is 0 during discharging, representing the operational modes, actually. And then once the temperature, once the internal energy of the water inside the thermal energy storage tank changes, this allows that the water exchange heat with the PCM inside the tubes. And most importantly, we also defined a load shifting index in order to measure, in order to quantify how much load we shifted from on-peak periods to off-peak periods by using the pre-stored heat inside the thermal energy storage tank. So this is the measure for us, how much time we did not operate, we did not need to operate the heat pump for the building heating. So the model validation can be seen in two steps. We compared the temperatures with the experimental data, water temperature on the upper left, and the lower left side, we also compared the average PCM temperature in the numerical model and actual PCM temperatures in the experiment. And we have seen that the largest discrepancy is 4 to 3 kelvins, depending on the water or PCM temperatures, and which is quite acceptable in this case. And secondly, we also compared the charging and discharging times in minutes, and we have seen that the largest deviation was 7.4%, which corresponds to the 7 minutes in the whole process, which we can also take acceptable. So coming to the results and discussion, we first compared the water temperatures on the left side. We can see that T5, T8, and T14. These represents the T5 and T8 are the temperatures in axial directions, and the T14 is in the radial direction. So in some other location, in the radial location near the wall of the thermal energy storage tank. So we can see that these temperatures are quite close to each other, which says us that the system can be treated as a lump system because the variation with respect to the location is negligible. And on the right, PCM temperatures measured from different points are shown, and we can significantly see the phase change process by isothermal temperature curves during charging and also during discharging. We have done this simulation, actually experiment in the 3 kilowatts on the right. I presented especially this one because we can see the phase change process more clearly. And continuing with the COPs, which represent the air source heat pump in this process. And we can see here a comparison with no PCM case and PCM case. And I would like to say that in the no PCM case, the tubes are not empty, they are filled with water. Therefore, we can also use water as a thermal energy storage material in the tubes. So that would be a more fair comparison. So inclusion of PCM into the thermal energy storage tank attained a higher temperature stability at the condenser of the heat pump with during a certain period, and therefore the compressor work mitigated and the average COP of the heat pump increased by around 19%. And thermal discharging decreased by up to 16% by using lauric acid in the experiments, which was actually not a desired situation because we want to extend the operational time, extend the heating time by using PCMs. However, the reason is that the PCMs have inherently very low thermal conductivity, which restricts them to make a rapid heat exchange between water and PCM. That's why they cannot solidify or melt rapidly, and therefore they cannot release the stored heat in the desired time. So, however, the load shifting index is improved, although the heating time is decreased. The load shifting index is improved by up to 10% using PCM. This is also attributed to this more stable working of the air source heat pump. So the numerical simulations show that, as you can see, the temperature curves on the left, and just below that, the liquid fraction curves. We can see the liquid fraction curves starts from 0, which means that the PCM is solid, and then goes up to 1, which means that the PCM is liquefied completely. However, on the return, when we try to heat the building with this stored energy, we can see that the liquid fraction curves cannot reach 0, which means that we have still an absorbed energy, a significant amount of thermal energy, which cannot be released due to low thermal conductivity. However, although the solidification could not be completed due to this phenomena, RT44HC, which means that high capacity, it has high latent heat capacity, among others, it released 68% of the stored energy, and even in this case, the amount of thermal energy release is almost twice as much compared to that of lauric acid, which we originally used in the experiments. So the numerical simulation says that RT44HC would be a better candidate for this application. And then we go further for this, and we calculated the charging and discharging times along with the load shifting index, and numerically obtained times for this thermal energy storage unit, and PCM with high latent heat capacity, such as RT44, helped extending heating time, meaning that the discharging time from the thermal energy storage unit by 4%, and the load shifting is improved by 6% due to this stability. In conclusion, I would like to say that using PCM is expected actually to extend the heating time. However, this can also have a different reaction because of this low thermal conductivity. However, we can see that the COP can be also improved, but here we should also pay attention that the tank or the storage container should be well insulated, because otherwise, with the heat losses, you can also have lower COP values because you need to operate the heat pump much more in a longer time. And the challenges here, as I repeatedly say, the low thermal conductivity. Using PCM is a really good option, a promising technology. However, the major barrier is the low thermal conductivity. We need to get over this. Therefore, the heat transfer enhancement techniques, such as using fins, extended surfaces, adding nanoparticles to the PCM, or using metallic foams in order to improve their effective thermal conductivity, should be recommended. If we have some opportunity to use heat transfer enhancement techniques along with PCMs, then we could recommend using PCM. Otherwise, if we are unable to use this kind of technology, this kind of techniques actually, we should also use water, which is also a good candidate for thermal energy storage. However, we can basically, at these temperatures, we store sensible heat into water. That's why the temperature goes higher. we should also pay attention that by using PCM, we can make this in nearly isothermal conditions. Thank you very much. I just tried to make it brief and concise to not take your time. Thank you very much.
Thank you, Mr. Yildiz. Any question?
Thank you for your presentation. Can you please explain us your numerical simulation? What kind of type numerical simulation did you use, and performance of numerical simulation that...
Okay, yes, surely. You're welcome. We have actually wrote an in-house code. So we developed it on Fortran basis, and we used the aforementioned differential equations to simulate, to actually represent the internal energy change of the water, as well as the heat exchange between water and PCM. Here, we should also use the heat transfer coefficient between the PCM and water. This heat transfer coefficient has negligible effect after a certain point. We actually verified this by using CFD simulations, which is not included in this work, but we have done some CFD calculations on some commercial softwares, and we can see that we obtained the heat transfer coefficient actually from these outcomes, and we tried at different values, and at the end, we have seen that the thermal resistance of the PCM is much higher than the thermal resistance outside, which means that of the water. So that's why the dominance is in the PCM side, and that's why the heat transfer coefficient has negligible effect after some value actually. And then we use in our code finite difference method to discretize the differential equations, and we used with a smaller time step to keep the Fourier number below 0.2, and we can write our code this way. You're welcome.
Hvala. Ovim bi završili današnje prepodnevno okupljanje. Ja bi voleo da... Thank you, Mr. Yildiz. That's for you.
Thank you very much.
Thank you. You're welcome. Samo jedna informacija. Znači, sada imamo pauzu nešto manje od sat vremena, pošto ste ostali vi izdržljivi do sada. Ja bih vas zamolio da pređete u restoran, tamo će biti neki koktel za izdržljive ljude na ovom skupu, a u 2 sata počinje nova sesija pod nazivom Zakonodavne opcije i politika o HFC-ima u Srbiji i evropska regulativa o F-gasovima. Tu će biti interesantnih par predavanja vezano za nove propise i F-gas regulativu, i oni koji se bave rashladnim fluidima će nešto novo saznati. Hvala vam još jednom, sve najbolje.